Dark matter. The invisible majority. You look up at a sky full of stars and think you're seeing the universe. But most of what holds those stars in place is missing from the picture. This series is about that missing part, the invisible majority we call dark matter, and the ways we've learned to trace what we cannot see. Across these chapters, we'll move from the big canvas to the fine grain. We'll take inventory of the cosmos and notice that ordinary atoms are only a small slice. We'll listen to galaxies that spin too fast for their visible mass. We'll weigh clusters the way Fritz Zwicky did and find more gravity than light can explain. Then we'll let gravity do a magic trick. We'll watch it bend light into arcs and rings, turning the sky into a lens that maps hidden mass. We'll visit the bullet cluster where hot gas goes one way and gravity goes another, and we'll read the baby picture of the universe, the microwave background, for patterns that insist the dark is real. We'll climb the cosmic web, compare it to giant simulations, and see why a cold, quiet scaffold builds the right mix of filaments and halos. We'll ask why stars, gas, dust, and even black holes can't add up to the whole story. Then we'll walk through the candidates, heavy partners that freeze out, whispering axions, warmer and self-nudging variants, and what happens if gravity itself asks for a small rewrite, and where that rewrite falters. From there, we head underground to rooms that listen for tiny taps in noble liquids and crystals. We scan the sky for the byproducts of invisible collisions. We visit colliders that try to make the unseen and spot it by the hole it leaves in the momentum ledger. We'll be honest about limits, what they rule out, and how three very different maps still point to the same islands of possibility. On small scales, we'll face the puzzles that keep us careful. The sharp versus soft centers of dwarfs, the brightest satellites that didn't show up when we expected them, and the faint companions we're still finding. We'll ask why galaxies need massive halos to keep their disks thin, their bars steady, and their star formation in long, readable sentences. We'll wonder whether dark matter can pile up near black holes, and whether a richer hidden world, dark photons, dark forces, quiet portals, might be whispering just beyond our current reach. We'll also look ahead. Rubin, Euclid, Roman, and CMBS4 are about to sharpen the lensing picture, steady the distance ladder, and weigh structure where galaxies are scarce. Better maps, tighter cross-checks, new detectors, smarter searches. Together, they narrow the paths until the right one remains. All along, the rule is simple. Keep it human and clear. No heavy math, no hand-waving. Just the best stories the data can tell, and the places those stories still have gaps. If you're new here, start at the beginning and let the case build. If you're returning, welcome back to the hunt. And one more thing. This series works best as a conversation. In each episode, I'll ask a question and read your answers in the next. Here's today's. What convinces you most that the invisible majority is real? The way light bends around hidden mass? The flat rotation of galaxy disks? The cosmic web matching our simulations? Or do you think gravity itself needs a tweak? Drop your take in the comments. Ready? Let's step into the dark and see what it reveals. Welcome. Hidden matter extended in 2, 3, 4 out 2, 3, 4, 5, 6. Let your shoulders soften and your jaw unclench. You're arriving at the edge of a question that quietly rearranged our map of everything. You look into a night so deep it feels like water. Stars are beads on a vast black thread, and yet the thread itself is the mystery. If we can't see it, how do we know it's there? Tonight, you and I will travel by clues. The way a sailor reads wind from the angle of a sail, or a tracker reads an animal from a pressed leaf. Start with a spiral. Imagine a galaxy like a slow pinwheel. A bright center, arms languidly swept outward. In a universe lit only by stars and gas, you'd expect a simple rule. The farther out a star is from the center, the slower it should orbit, because there's less visible mass inside its circle to pull it in. But when astronomers actually measured those speeds, the rule broke. The outer stars refused to slow down. In galaxy after galaxy, the rotation curves flattened, staying far beyond where the light could account for the pull. In, 2, 3, 4 out, 2, 3, 4, 5, 6. You don't see the hand. You see the grip. That steady speed is the handwriting of something unseen. A halo of matter, spread wide, massive and quiet. Not a thin ring of mystery, but a great dim sphere cradling the visible galaxy like a lantern inside a glass globe. In this picture, most of the galaxy's mass lies outside the shining arms, extending well beyond the last outlying stars. There's a humility in learning by inference. In daily life, you already do this. You read the weather from the smell of rain, the mood of a friend from the space between their words. Here, the universe becomes the friend. The curve of the graph becomes the pause in the sentence, and everything in you learns to listen. Slide your attention to a different clue. The way space bends. Einstein told us that mass curves space-time, and light follows those curves. Put a massive cluster of galaxies between you and a more distant galaxy, and the nearer cluster acts like a lens, gravitational lensing, distorting, magnifying, even splitting the background light. Sometimes the distortion is subtle, a gentle stretch no one notices until a computer tallies the bias across thousands of galaxies. Sometimes it's dramatic, arcs, rings, mirages of the same background object. When astronomers weigh a lensing cluster two ways, once by the light they can count, and once by the strength of the lensing, the second weight comes out heavier. There's extra gravity in the glass. The lens is thicker than it looks. The invisible is tugging on the visible, reshaping the path of light across millions of light years. In, 2, 3, 4 out, 2, 3, 4, 5, 6, you might ask. Are we sure it's not gravity itself that needs rewriting? Scientists keep that door open. They test the hinges, check the frame, and still, multiple lines of evidence point to the same conclusion. Galaxy rotation says there's hidden mass. Lensing maps say there's hidden mass. The dance of galaxies inside clusters says there's hidden mass. And the afterglow of the Big Bang, the cosmic, microwave background, whispers a consistent story about how much of each ingredient the early universe contained to grow the cosmic web we see today. Think of the large-scale structure like a fog of matter collapsing into threads and knots, filaments and clusters. Simulations that include an invisible, slow-to-interact component grow galaxies that look like ours. Spirals and ellipticals strung along filaments, clusters at intersections. Remove that quiet scaffolding, and the universe struggles to form this pattern on time. Out. 2, 3, 4, 5, 6. Pause here. Let invisible shift inside you from meaning imaginary to meaning quiet. Dark matter doesn't shine, doesn't bounce or gulp down photons the way dust or gas does. It drifts through light almost as if light isn't there. It leaves no glow in a telescope, no heat on a detector. What it leaves is shape. The firm grip that holds a galaxy together at the edges. The unseen bulk that turns space-time into a lens. The scaffold that helps ordinary matter gather and ignite. Listen to one more clue. Galaxy clusters that have collided, like two swarms passing through each other. The hot gas, ordinary matter, slams together, heats up and lags behind. But the main gravitating mass, traced by lensing, sails ahead with the galaxies as if it barely noticed the crash. That separation tells us the dominant mass isn't the gas we can see. Whatever carries the bulk of gravity, there doesn't interact much with itself or with light. It passes through, aloof and steady. It's 2, 3, 4 out, 2, 3, 4, 5, 6. Now step gently into numbers, simple ones. If you gather all the cosmic ingredients, ordinary matter, the kind that makes stars, planets, oceans, you, turns out to be a minority. The lanterns and their oil are not most of the weight. The hand that holds them is, and beyond even that lies dark energy, a different mystery. But we're not rushing there tonight. Your attention is a candle. Let it burn one wick at a time. History helps. For much of the 20th century, astronomers were building better instruments and better questions. The story of flattened rotation curves came into focus through careful, repeated measurements. It wasn't a single dramatic snapshot, but a chorus of galaxies, each singing the same stubborn note. The outskirts are moving too fast to be held by light alone. That note, heard across different instruments and teams and eras, is what turned a whisper into a pillar. Out. 2, 3, 4, 5, 6. You may wonder what dark matter actually is. For now, it's a field of candidates rather than a face. Some ideas imagine new kinds of particles, massive but shy, passing through most matter unfelt, revealing themselves only by gravity. Others point to lighter, wave-like possibilities that hum softly across space. Experiments on Earth listen in underground halls and in the cold of space, trying to catch the faintest tap on a detector. So far, the universe keeps its quiet, but science is patient. You breathe with that patience now. I've been 2, 3, 4 out. 2, 3, 4, 5, 6. It's okay not to know the name of a thing while you are learning its shape. You can know the outline by touch. Gravity gives you that outline. A halo wrapped around each galaxy, a deep well at the heart of clusters, a web that underlies the placement of everything luminous. If the visible universe is the melody, dark matter is the key the music sits in. Change the key and the song falls apart. Look back at our own galaxy for a moment. The Milky Way spins inside such a halo. Stars, gas, dust. The ribbon you see with your eyes on a clear night are the bright skin of something broader. The halo extends far beyond the outermost visible stars, a great dim embrace. The sun orbits in that embrace, 26,000 light-years from the center, part of a dance choreographed by what does not shine. In. 2, 3, 4 out. 2, 3, 4, 5. And there's a feeling that comes with this knowledge, something like perspective, something like kindness. The universe reminds you that the obvious is not the whole. Many truths you live by announce themselves indirectly. The care someone shows you in small consistencies, the way a city's mood shifts with the first rain, the peace in your body after a long breath. Dark matter is that kind of truth writ cosmic, not a ghost story, but a patient story. Soon we'll trace the evidence in detail. The measured rotation curves that first raised eyebrows, the lensing maps that sketch what our eyes can't, the fingerprints in the early universe's afterglow, and the leading ideas about what this quiet majority might be. We will visit candidates, some heavy and nearly silent, some whisper-light and wave-like, and meet the experiments listening for each. We'll see how galaxies need this unseen partner to grow, and how the cosmic web emerges from its scaffold. For tonight's welcome, it's enough to hear the pattern, enough to know that reality is larger than the light it wears. You can rest in that without closing the question. Curiosity doesn't demand urgency. It asks for presence. Let the unknown be a spacious room you learn by walking through slowly. Out. 2, 3, 4, 5, 6. As you exhale, feel yourself held by the same quiet architecture that holds the stars. What you can't see is not your enemy. It is the context. You and I will keep looking with gentle attention, and the universe will keep answering in its own fluent way. Not with a shout, but with a gravity that writes its signature everywhere. Good, let's keep going. Cosmic inventory in. 2, 3, 40 out. 2, 3, 4, 5, 6. Let your breath find an easy cadence. Picture a quiet work table and a simple round pie. Tonight, we label the slices of everything, what the universe is made of by percent, not by poetry. Begin with the small slice that feels enormous to us, the hum of 5%. This is normal matter, ordinary in the sense that it talks to light, atoms, protons and neutrons in the nucleus, electrons in their fuzzy probable shells. This is you and oceans, stars and planets, trees and telescopes, the dust that turns sunsets orange, the gas that forms new suns. If a photon can bump into it, warm it, scatter off it, glow from it, chances are it lives in this thin, bright slice. In 2, 3, 40 out. 2, 3, 4, 5, 6. And yet, all that brilliance is minority. The rest of the pie is invisible in two different ways. One way we call dark matter. It's matter in the gravitational sense. It clumps, it weighs, it gathers light into galaxies, but it doesn't glow or block or shimmer. It barely speaks to photons at all. Think of dark matter as the scaffolding that ordinary matter climbs. Without it, galaxy disks would fly apart at the edges. Clusters would not hold their swarms. We don't see the scaffold. We feel the stability it grants. Different surveys tell a consistent story. This quiet weight makes up a much larger slice than the things that shine. The other way is stranger still. Dark energy. Not a weight that gathers, but a pressure that pushes. It doesn't form halos or clumps. It acts everywhere at once, woven into the fabric of space itself. And rather than pulling things together, it seems to accelerate the expansion of the universe, urging galaxies to drift apart faster over time. If dark matter is the firm hand that holds galaxies together, dark energy is the soft, steady push between them in 2, 3, 40 out. 2, 3, 4, 5, 6. How do we know the sizes of these slices? We don't crack open the cosmos like a fruit. We weigh it by its effects. Clue 1. The afterglow. The cosmic microwave background, the universe's baby picture, carries a faint, dappled pattern in temperature. Those ripples are like frozen sound in the early plasma, pressure waves ringing through a hot fog of particles and light. By measuring the spacing and heights of those ripples, we infer how much stuff was present to ring, and how gravity and pressure balance the notes. It's like hearing a song and deducing the room it was recorded in. The pattern prefers a recipe with a small slice of ordinary matter, a bigger slice of dark matter, and a large backdrop of something that doesn't clump at all. Clue 2. The cosmic web. On scales of hundreds of millions of light years, galaxies thread into filaments with vast voids between. Computer simulations that include dark matter grow a web that looks like ours. Knots where clusters sit, strings where galaxies align. Remove the dark matter slice and the web phrase. Structures form too slowly or in the wrong amounts. Clue 3. The expansion story. When we watch distant type Ia supernovae, standard candles that tell distance by their intrinsic brightness, we find they're dimmer than a just gravity universe would predict. Space has stretched more than expected, as if a hidden term in the equation were pressing outward. This is the signature of dark energy, not a local push, but a global habit. In 2, 3, 40 out. 2, 3, 4, 5, 6. Pause and let the idea settle. Most of reality, by percent, is not the part that gives us sunsets, that can feel disorienting. But there's a calmness inside it too. Your life already works this way. Much of what shapes a day is quiet background. Sleep, gravity, habit, air, rarely noticed directly, always decisive. The universe is similar. The showy 5% is balanced on vast, unseen context. A little nuance helps. When we say 5% normal matter, we're counting the mass-energy budget today. Photons, the actual light, are a smaller fraction still, cooled by expansion. Neutrinos, the fleet and shy cousins of electrons, are present too, but they carve only a sliver of the pie. What dominates the budget are the three big actors: ordinary matter for things and light talk, dark matter for invisible weight, dark energy for the quiet acceleration of space itself in 2, 3, 40 out. 2, 3, 4, 5, 6. If you like numbers, you can hold them loosely, round them so your mind can breathe. Think 5% ordinary, a quarter to a third dark matter, about 2/3 dark energy. Don't chase the decimals. Let the proportions do the lesson. A thin slice makes stars. A thicker slice holds them. The larger slice sets the stage's tempo, stretching the stage as the play goes on. What does each slice do? Ordinary matter, 5%, talks with light. It cools, collapses, forms chemistry, builds worlds, writes poems. Because it interacts with radiation, it can shed energy and settle into disks and clouds. That's why galaxies have visible shapes. Dark matter, the quieter, heavier slice. mainly interacts through gravity. Because it doesn't shed energy by glowing, it stays puffy and halo-like, embracing galaxies in vast spheres. It deepens the wells that ordinary matter falls into, making galaxy formation efficient and early. Dark energy, the largest, gentlest slice, doesn't clump. It seems uniform, like a property of space itself. Its effect grows as space grows, so the later universe feels more of its influence than the earlier one. Result: on the grandest scales, galaxies not bound together drift apart faster and faster. Out. 2, 3, 4, 5, 6. This raises the human questions. Will the expansion run away forever? Will the sky continue to thin as distant galaxies slip beyond view? We don't press for certainties tonight. We notice the honest state of things. Our models fit the data well, yet the names dark matter and dark energy are still placeholders for deeper understanding. They're not decorations. They're working labels for real measured effects. The inventory is measured. The identity is the adventure in 2, 3, 40 out. 2, 3, 4, 5, 6. There's comfort in the way the evidence agrees from different angles. The afterglow's ripples, the web's architecture, the lensing weight of clusters, the drumbeat of supernova distances, the way galaxies spin. Each method has its own biases, its own instruments, its own teams across decades. And yet the pie keeps coming out the same shape. When different eyes see the same outline, you can trust the outline even while the details sharpen. Let's bring it back to your night sky. The starlight that reaches you is old and small in the grand accounting. A thin, luminous rind on a much larger fruit. But small does not mean unimportant. The 5% is where complexity blooms. It's where elements learn to braid into molecules and minds. It's where questions wake up and ask for the rest of the pie. Out. 2, 3, 4, 5, 6. And there's a gentle philosophy in that. You are made of the minority slice, and yet your attention can hold the whole. You don't have to be most of the universe to be in conversation with it. Curiosity is a bridge proportion can't measure. Soon, we'll travel deeper into each component. We'll watch how dark matter's scaffolding shapes galaxy rotation and cluster collisions. We'll sit with the evidence for dark energy and what it means to live in an accelerating cosmos. We'll honor the normal slice by following atoms from furnaces in stars to the breath in your chest. For now, keep the picture simple and clean in your mind. A pie with 3 meaningful slices. A bright 5% that speaks in photons. A quiet, heavier share that holds shapes together. And a wide, soft pressure that sets the pace of expansion in 2, 3, 40 out. 2, 3, 4, 5, 6. As you exhale, imagine the universe balancing those shares with patient hands. What you are is a bright sliver. What you're held by is vast and calm. And in the middle of that balance, a thought as steady as starlight. Knowing the proportions is not the end of wonder. It's the beginning of better questions. Good. Let's keep going. Dark sectors and portals. Dark photons, hidden forces, and the idea of a richer unseen world. We've often treated the dark as quiet ballast, a cold scaffold that pulls but barely speaks. What if that's only the surface? What if the dark has its own particles, forces, and chemistry, mostly sealed off from us except through a few narrow links? That is the idea of dark sectors and portals, a hidden world that interacts with ours by small, specific couplings. Picture a second stage behind the curtain. Dark matter is just one actor there. Others might include a dark photon, a sibling of our photon that talks to dark charge, and a dark Higgs, setting masses in that sector. Some residents are stable, others fleeting, busy with each other, shy with us. The curtain is thick but imperfect. Along its hem lie portals that let faint whispers pass. 4 common portals. Vector portal, our photon, and a dark photon mix, slightly. Kinetic mixing. To us, the dark photon looks like a light vector boson produced in collisions. decaying to visible particles or slipping away invisibly. Scalar, Higgs portal. Our Higgs mixes with a dark scalar, allowing energy exchange between sectors and opening exotic Higgs decays or long-lived scalar signals. Neutrino portal. Sterile, right-handed neutrinos mix weakly with known neutrinos, providing a bridge to otherwise hidden states. Axion-like portal, for completeness, an ultralight field that can solve problems in our sector and communicate with dark stories. 2. Why consider a richer hidden world? Because it can ease small tensions without breaking what works. Light mediators can give dark matter self-interactions that soften dwarf galaxy cores without ruining clusters. Mild dark sector cooling can reshape tiny halos and satellite survival. A dark Higgs can tweak early universe freeze-out, and small but non-zero portals offer concrete places to search. How to listen for whispers. Colliders. Look for missing energy plus a tag, mono X, or displaced decays. Tracks that start centimeters to meters from the collision point. A dark photon may yield a tight Axion pair away from the primary vertex. Higgs dark scalar mixing can produce invisible Higgs decays, or late soft sprays. Fixed target and beam dump experiments. Fire intense electron-proton beams into a dump. Ordinary particles get absorbed. Weakly interacting states pass through. Downstream, search for regenerated Ipuan pairs or subtle electron recoils. Rare decays and precision tests. Mesons or taus can take unusual branches if a portal is open. Small deviations in magnetic moments or parity-violating scattering constrain new mixings. Astrophysics and cosmology. Stellar cooling. Supernova energetics. Galaxy shapes. The bullet cluster. Big Bang nucleosynthesis, the CMB, and the effective number of light species, N Welch text F, all limit how loud a portal can be. Think of the dark photon as a barely audible radio station. The signal exists, but you must tune beam energy and geometry just right. For a dark Higgs, imagine two violin strings nearly in tune. A little mixing lets energy pass, sometimes as invisible Higgs decays, sometimes as faint tones that last a touch too long, displaced vertices. Not all dark matter need be heavy. Subgiv candidates might not budge xenon nuclei, but they can nudge electrons. Portals open new detection channels. Electron ionization in crystals or noble liquids. Tiny heat packets in superconductors or superfluid helium. And missing mass techniques at accelerators. The same vector portal that produces dark states in a beam dump can give them just enough electric echo to tap an electron underground. Do portals help with cosmic puzzles? They can. Velocity-dependent self-interactions soften dwarf cores while sparing clusters. Gentle dark cooling can seed compact clumps that perturb stellar streams. Partial thermal contact in the early universe broadens viable paths to the observed relic abundance. The caution is balance. The dial that cures one issue can overcorrect another. Hence, the field values complementarity. Colliders, intensity experiments, precision tests, direct detection, and astrophysical probes cross-checking one another. Why no discovery yet? Because the links are intentionally tiny. We're searching for drafts in a quiet house. Carry a candle room by room. Watch the flame at every seam. Each constraint seals a gap. Each new instrument is a finer candle. If a breeze exists, the flame will flicker somewhere. Maps of the hunt. Accelerators. Flavor factories and soft trigger runs. Maplight. Weakly coupled regions. Big rings chase heavier mediators via missing energy and displaced tracks. Intensity frontier. Beam dumps. Fixed targets. Neutrino near detectors. And quiet underground halls probe feeble portals with huge statistics and low backgrounds. Precision frontier. Magnetic moment anomalies. Rare decays. Parity violation measurements limit how strongly new vectors and scalars can mix. Astrocosmo frontier. supernova cooling, stellar lifetimes, galaxy profiles, and structure growth fence off large swaths of parameter space. 3 compact case studies. Light-dark photon, MeV-GeV, with tiny mixing, living centimeters-meters before decaying to E prime. Colliders see displaced dielectrons, beam dumps see delayed peaks, rare decays show small kinks. Stellar and early universe bounds press from both sides, leaving a narrow but interesting band. Dark Higgs mixed with ours. If below MH2, the visible Higgs gains an invisible branching. If above, expect a quiet scalar resonance with unusual, sometimes long-lived decays. Cosmology prefers early decays. Detectors love lifetimes that leave tracks. Sub-GeV dark matter, plus light mediator. Direct detection pivots to electrons, hush phonons. Accelerators use missing mass peaks. Fixed targets seek elastic scatters downstream, while slipping past supernova and early universe limits. Pitfalls. Small and late signals attract backgrounds. Photon conversions in detector material. Cosmic muons, low-level radioactivity, or messy astrophysics. Defenses include redundancy, multiple targets baselines, beam-off checks, blinded analyses, and focusing on quiet astrophysical environments. Dwarf galaxies, old stars, clean transients. What would success look like? Not a single shout, but a chorus. A repeatable excess of displaced Absch pairs in a fixed target hall at one mass. A matching kink in a rare meson decay, a compatible displaced signature at a collider, and electron recoils underground with the predicted rate and spectrum. No one plot screams. Together, they rhyme. Hold 3 images. 2 cities at night with a few narrow bridges. The traffic is scant but real. We watch the bridges, a whispering gallery where a soft word rides the curve. Portals are those curves. A tuning dial. Static, then a narrow slice where signal stands up. Confirm with a second and a third radio. So when you hear dark sectors and portals, translate simply, the dark may be a landscape, not a lone stone, speaking through narrow passes. We learn that land by walking every pass, beams into dumps, colliders tuned for late sparks, rare decays, low threshold sensors, and the sky's quiet constraints, until one path carries more than a breeze. If that day comes, the scaffold that holds galaxies becomes an ensemble, still harmonious, just richer than we first guessed. Weak lensing maps. Tiny shears across the sky reveal the web of mass. Begin with a simple truth. Light is honest about the shape of space. When light from faraway galaxies crosses the universe, it passes hills and valleys made by mass. Stars, gas, and the quieter weight we call dark matter. Each hill or valley nudges the path a little. One nudge is too small to notice, but when you look at millions of distant galaxies, a pattern appears. That pattern is weak lensing. Picture a field of distant galaxies as a meadow of tiny ovals. In a perfectly calm universe, their orientations would be random, like leaves scattered by a playful wind. In our universe, the leaves show a faint preference. Over large patches of sky, those tiny ovals are stretched in the same gentle direction, as if a soft hand had brushed them all at once. That faint, consistent stretch is called shear. It is the imprint of foreground mass on background light. Weak lensing is subtle by design. Individual galaxies are already a bit oval on their own. That makes each one noisy as a messenger. The power comes from numbers. You don't listen to a single leaf. You listen to the meadow. Astronomers measure shapes for huge populations of background galaxies, correct for blurs from the telescope in the atmosphere, and stack the results. Out of all that averaging, a map emerges. Where the sky stretches a little more in one direction, you infer more mass in front. Where it relaxes less. This is how we draw the web of mass without needing it to glow. There are 3 levels to keep in mind. First, the small-scale view around a single massive object. Stack many background galaxies behind many foreground galaxies, and a pattern appears, a gentle ring of stretch around the foreground ones. That pattern outlines their invisible halos, how far they extend beyond the visible stars, how the grip fades with distance. This is galaxy-galaxy lensing, a quiet way to weigh halos too dim to see directly. Second, the cluster scale. Around a massive cluster, background galaxies line up as if combed by a wide brush. The shear is stronger near the crowded core and softer farther out. By reading how the pattern changes with distance from the center, you map the cluster's mass from the bright heart to the dim outskirts, finding where the weight actually lives. Often, it stretches well beyond what the cluster's light would suggest. Third, the wide field, all-sky view. Spread your net across hundreds or thousands of square degrees and measure those tiny shears everywhere. The pattern you recover, often called cosmic shear, sketches the great web of structure that links galaxies into filaments and knots, with deep voids in between. This wide pattern is sensitive not only to where mass sits, but also to how structure has grown over time. In that sense, weak lensing becomes a weather report for the history of the universe. How fast the web thickened, how clumpy it became, and how the quiet push of cosmic expansion competes with gravity's pull. Weak lensing is both generous and demanding. It is generous because it listens to all mass equally. Stars count, gas counts, dark matter counts. Anything with weight leaves the same kind of fingerprint on light. It is demanding because the signal is delicate. Telescopes blur, atmospheres shimmer. Cameras introduce tiny twists. Even the way a galaxy forms can give it a preferred shape unrelated to lensing. To trust the map, astronomers learn each of these habits and subtract them carefully. They check the same patch of sky in different ways. They rotate shapes to make sure false patterns cancel. They compare results from different instruments. When the same web appears through all the checks, you can believe it. What does the web look like? Imagine a continent seen from high above at night. Bright cities mark clusters. Fainter roads connect them like filaments. Dark countryside lies between, the voids. Weak lensing draws the same style of map, but it is a map of mass, not light. Sometimes the bright city of light and the heavy city of mass overlap closely. Sometimes the mass city sprawls wider than the lights, telling you that most of the holding is done by the unlit. The roads, those filaments, are especially revealing. They are hard to see in starlight alone, but rise out of the sheer pattern with quiet confidence. The web is not only a picture, it is a test. Different ideas about the universe predict different levels of clumpiness. If gravity gathers matter quickly, the web thickens early. If a gentle cosmic push spreads things apart faster, the web grows more slowly. Weak lensing reads the balance by measuring how strong the shear is at different distances. Nearby, middling, and far, we learn how structure has changed with time. That history, in turn, tells us about the character of dark matter and the pace of cosmic expansion. There is also a practical gift. Weak lensing helps us weigh the unseen parts of ordinary things. A galaxy may look modest in light, but sit inside a surprisingly large halo. A cluster may look crowded, but hold even more mass in a wide, dim envelope. Lensing lets us measure these halos without guessing how stars formed, how dust hides, or how gas flows. We simply read the stretch of background galaxies and let light tell us what mass has done. If you like simple images, keep these close. Think of fingerprints in clay. Press your hand lightly and pull away. The print is shallow, but it's there. Weak lensing is the shallow, widespread print of mass on the sky. Think of ripples on a wheat field. A single stalk bends for many reasons, but 1,000 stalks bent the same way tell you about the wind. Weak lensing is that 1,000-fold agreement. Think of a soft map drawn with a smudge pencil. You don't see sharp borders, but the shapes are unmistakable. Here a ridge, there a valley, and long, faint roads between. Weak lensing draws with a smudged pencil, yet the terrain is clear. Weak lensing also works as a bridge between scales. On the smallest, brief brightening events can reveal wandering compact objects. On the middling scale, stacked shears weigh halos. On the largest cosmic shear charts, the web. Across them all, the same rule holds. Light is loyal to mass. There are limits. Weak lensing does not tell you everything at once. It is less precise about exact depths along the line of sight. It prefers breadth over sharp edges. That is why it pairs well with other clues. Combine it with the bending seen in strong lensing near dense centers, and you get a portrait that is sharp at the core and smooth at the edges. Combine it with counts of galaxies and their colors, and you learn how light traces weight. Combine it with the faint pattern in the oldest light, and you test whether the same recipe explains both the early rumble and the present-day web. For dark matter, the lesson is steady. You do not need it to shine to see that it is there. Weak lensing shows halos around galaxies that would otherwise look too small to hold their companions. It reveals cluster envelopes that extend far beyond the bright crowd. It outlines filaments where little or no light gathers. Yet the stretch says, softly but firmly, weight lives here. When you stack all these maps together, you find the quiet majority everywhere, in halos, in bridges, in the background scaffolding that gives the luminous universe its shape. There is a softer reflection inside this science. Much of what steadies a life is not the loudest part: sleep, habit, kindness, the background rhythm of ordinary days. These are weak forces in the moment, but over time, they set the shape of everything. Weak lensing is that wisdom at cosmic scale. The tiny shears don't shout, they whisper in chorus, and the chorus draws a map you can trust. So when you hear weak lensing maps, translate it into something clear and human. Millions of small stretches pointing, together, toward where the universe keeps its weight. It is a way to weigh without touching, to see without light, to sketch the roads between the cities of stars. And with each new survey, each deeper image, those roads come into better focus, revealing the web that holds galaxies in place and teaching us how the quiet architecture of dark matter shapes the unfolding story of the sky, axions and fuzzy halos. You step into a puzzle that began not with galaxies, but with the strong force, the force that binds quarks into protons and neutrons and holds the heart of every atom together. The theory that describes this force seems to allow a tiny built-in twist, a kind of internal lever that would tilt the rules and make the strong force treat mirror images differently. If that lever were set anywhere but almost exactly zero, you would expect the neutron to carry a small electric preference, a measurable lean to one side. Experiments keep looking for that lean and keep finding nothing, or so little. It is hard to believe the lever was left so perfectly aligned by accident. This is the strong CP puzzle. Why is the lever set so precisely to neutral? A graceful idea answers, don't assume the lever is fixed. Give it a spring that naturally relaxes it to zero. That spring is a new field pervading space, and the gentle vibration of that field is a new particle, the axion. In this picture, the universe doesn't need exquisite luck. It has a built-in thermostat. If the strong force tries to twist, the axion field slides the setting back to neutral. The neutron stays untilted. The puzzle softens into a story about balance. Once you let that new field into the universe, a second door opens. Fields don't just solve equations, they carry energy, and in the young cosmos that energy can behave like a sea of particles. As the universe cools, the axion field can start to oscillate in place, like a drumhead settling after a strike. Those oscillations don't radiate away easily, they coast. That means a huge reservoir of cold, quiet matter can appear without ever needing hot collisions to make individual particles one by one. You haven't only solved a symmetry riddle, you may have found the invisible mass that holds galaxies together. Picture two versions of the axion story, one familiar, one more exotic, both living under the same roof. In the first version, the axion is extremely light, but still acts like a cold, quiet gas of particles. Its presence is everywhere, but its individual quanta are so feeble that they drift through light and ordinary matter almost unnoticed. Halos of these axions form around galaxies, just as halos of any cold, non-glowing matter would. This is the classic axion as a dark matter candidate born out of a solution to the strong force puzzle. In the second version, the axion is so unbelievably light that its wave nature spills across vast distances. Here you stop thinking of marbles and start thinking of water. The axion behaves less like a swarm of discrete particles and more like a single, coherent wave that fills a halo. The wavelength can stretch across a good part of a galaxy, making the dark matter fuzzy. In that fuzzy regime, the wave can't be squeezed arbitrarily tightly. On the smaller scales, the wave pressure gently resists compression, smoothing out tiny clumps that would otherwise form. Dwarf galaxies in such a universe would tend to have softer, more chord centers rather than steep, needle-like peaks of density. The smallest, faintest satellites would be fewer. The web would remain, but the finest embroidery would blur. You can hold the difference with a simple picture. Cold, ordinary dark matter is like a desert of sand grains. You can pile sand into sharp cones. Fuzzy axion dark matter is like fog. You can gather fog into hills, but the crests round off. The result is a halo with a soft heart, a central solitonic core, surrounded by wavering interference patterns that flicker as the wave overlaps with itself. On a long timescale, those flickers look like a persistent graininess in the gravitational field, a tremor that can stir the orbits of stars ever so slightly. What would you see if this fuzzy picture were true? In small galaxies, you might find central regions that are smoother and wider than the sharp cusps predicted by a simple, all-sand universe. You might count fewer ultra-tiny satellites than a pure sand model would produce. In the thin gas that lies between galaxies and absorbs starlight from even more distant quasars, you might read a more gentle, smoothed-out pattern of ripples. Because waves that are truly vast do not permit the smallest wrinkles to grow. The universe, however, answers in layers. Some observations seem to like the gentle smoothing. Others demand more fine detail than a fully fuzzy cosmos would allow. The upshot is balanced and honest. A purely fuzzy version that fills the entire dark sector is squeezed into a narrow corner by current data. A partly fuzzy mix remains possible, and variations on the axion theme, axion-like cousins with different ties to the strong force, are actively explored. The idea is not a yes or no switch so much as a dimmer with positions still to test. While telescopes weigh halos, laboratories on Earth try to hear the axion directly. The trick is to coax that nearly silent field into making a whisper of ordinary light. In one approach, you place an exquisitely tuned metal cavity in a strong magnetic field and dial the radio through frequencies where an axion could convert into a tiny microwave photon. You listen and you wait. The tuning moves slowly. The quiet must be immaculate. Over years, these haloscopes sweep through deeper and deeper ranges, turning theoretical targets from wishful sketches into reachable stations on the dial. Another approach is to point a purpose-built instrument at the sun. If axions are born in hot stellar cores, some of them could stream outward and convert to X-rays in a strong laboratory magnet. A helioscope watches for that faint glow. Future instruments plan larger magnets, colder detectors, and cleaner optics. Ways of asking the same patient question with sharper ears. There are other inventive ideas. 2. Broadband coils that look for a magnetic whisper rather than a microwave tone. Tiny toroids wound like musical instruments. Shiny surfaces meant to coax axions to shed a sliver of light. The common spirit is simple. If a field is there, let it talk in the language we can hear. Astronomy joins the listening party. Stars can cool by emitting undetected particles. If axions couple to the right ingredients, they would slightly alter the lifetimes of certain stars or change the way white dwarfs shed their heat. Careful surveys of stellar populations turn those life cycle tweaks into limits on how loudly the axion is allowed to speak to matter and light. Meanwhile, black holes, those stubborn keepers of silence, offer a different kind of test. A cloud of ultralight waves can grow around a spinning black hole and sap its rotation in a process with a name that sounds like fiction but is deeply physical. If we survey many black holes and find spins that should have been erased by a certain axion mass but are still there, we close off that mass range. Slowly, the map of allowed territory becomes a patchwork quilt stitched by telescopes and labs together. At human scale, here is the narrative that matters. The axion began life as an elegant fix for a symmetry riddle in the strong force. That fix naturally creates a quiet sea that could be the dark. If the action is of the classic kind, it behaves like a cold, invisible gas that clumps into halos. If it is far lighter still, it behaves like a galaxy-sized wave that smooths the tiniest structures and rounds the hearts of dwarfs. Each version offers crisp, testable signatures. Each version has already faced serious tests, and yet the door remains open enough to keep the lights on in both the telescope dome and the underground lab. You can carry the heart of the axion story in 3 images. First, a thermostat. Whenever the strong force tries to twist, the axion responds like a spring, relaxing the setting to neutral. Balance restored. Second, a sea at dawn. As the cosmos cools, the axion field begins a long, slow swell. The swell does not break. It persists as a calm background, a reservoir of quiet mass. Third, a soft-edged lantern. In ultralight form, the axion halo is the glass that refuses to sharpen to a point. The light inside can flicker, but the glass keeps the glow rounded at the center. So when you hear axions and fuzzy halos, translate it into something clear and human. A single idea, born to solve a deep symmetry problem, may also explain a deep gravitational one. If the axion is merely quiet, it can be the dark in the usual sense. If it is ultralight, it becomes a wave that smooths the cosmos's smallest threads. Either way, the universe has given us a path to listen, through tuned cavities, patient magnets, careful star counts, and the shapes of the tiniest galaxies. And through that listening, a field that once lived only as an elegant repair might yet step forward as the invisible stage on which the visible plays. Black holes and dark spikes do hallucide early giants. Can dark matter pile up near black holes? Stand at the dawn of galaxies. The sky is young. The first stars have barely lit. Yet we already find beacons that should be impossible. Black holes 1 billion times the sun's mass, shining less than 1 billion years after the beginning. How do you grow something so heavy so fast? One answer is quiet but sturdy. Halos, the dark scaffolds that gather gas, keep it bound and set the terms of inflow. Another answer is sharper and more local. Near a black hole could dark matter itself spike, rising to a steep, bright density that changes the story of growth and glow. Begin far from the center. A halo is a catcher's mitt. It gathers gas along filaments and keeps that gas from escaping after the first fireworks. In tiny halos, gas cools through fragile molecules and forms small, hot stars that explode early. In atomic cooling halos, big enough to cool without those molecules, gas falls in more smoothly. If the halo's spin is low and its interior stays warm enough to prevent fragmentation, a large single object can collapse at the center. A direct collapse seed, already tens or hundreds of thousands of solar masses. With a head start like that, the road to an early giant feels less impossible. Sometimes the seed is smaller, the remnant of a first-generation star collapsing into a black hole of a few tens of solar masses. Alone, such seeds would grow too slowly. But halos help here too. They deliver fresh gas in cold streams. They host mergers that shake the center and loosen angular momentum. They keep the circumgalactic medium around, so when feedback pushes gas out, the gas does not vanish. It cools, turns, and rains back. In that dance of outflow and return, a black hole can spend long stretches near the Eddington limit without being snuffed out by its own light. There is a narrow path where growth can be super Eddington for a while, if inflow is thick and chaotic enough that radiation is trapped and carried inward. That path is risky. Too much heat and the supply blows itself apart. But halos tilt the odds by stabilizing the outer flow. The message from many simulations is not that one trick does everything. It is that several modest aids line up. Massive or fast-growing halos, a lull in early star formation, a background of ultraviolet light that suppresses fragile cooling, a stream of gas that stays dense and arrives with the right spin. All of these help a central seed bulk up quickly, then coast. Halos also decide whether growth lasts. A small halo is easily rattled by neighbors. A single strong burst of star formation can lift much of its gas away. A larger halo absorbs blows. It damps sloshing, holds onto the hot atmosphere that keeps the supply timed, and lets the disk rebuild between storms. If the seed sits at the focus of such a halo, the feeding line survives for many cycles. Even when a merger jolts the system, most of the orbital energy is bled into the dark outskirts rather than the bright core. So the disk is bruised, not broken, and the fuel keeps arriving. The earliest giants likely grew where halos were not only massive, but also well fed by the cosmic web and sheltered from lines of sight that would have stripped their gas. So yes, halos seed early giants, not by becoming black holes themselves, but by setting the scene for runaway growth. They make space for large seeds, protect the supply, recycle what feedback expels, and cushion the blows of a busy neighborhood. They do not guarantee a monster by dawn. They make it possible. Now drop toward the center and ask a different question. Can dark matter itself pile up around a black hole and form a spike? A steep rise in density that changes motions and signals. Imagine a black hole slowly growing at the heart of a calm, cuspy halo. If the growth is adiabatic, gentle compared with orbital times, the dark particles adjust their orbits inward. Phase space compresses. The density near the hole rises into a spike, steeper than the original cusp. In the simplest picture, the spike extends from just outside the region, where the black hole's pull dominates, outward to where the halo resumes control. In that zone, the dark density can become high enough that, if dark matter annihilates, it would glow in gamma rays far above the baseline. But galaxies are not meditation halls. They merge. Bars stir their centers. Stars scatter on new orbits. And black holes themselves collide. Each of these heats the central region, smearing out the spike. A binary black hole slurps nearby orbits during its in-spiral and leaves a core where the spike might have stood. A long-lived bar shakes the central halo, trading angular momentum and softening steep features. Even if a spike forms, encounters with dense star clusters and giant molecular clouds can erode it over time. What survives depends on the history. Quiet growth preserves structure. Noisy growth sands it down. There are, however, special places where spikes could be resilient. Around intermediate mass black holes, those that may live in dwarf nuclei or dense clusters, the environment is gentler. If such a black hole sits in a small halo with a history of few major mergers, a spike could persist for a long time. Even more speculative are mini-spikes around primordial black holes, if any exist. In those cases, the black hole is born into the dark fluid itself. The spike would be a fossil of that origin. How would we know? Several clues are on the table. First, indirect light. A steep spike in an annihilating dark sector would produce a compact excess of gamma rays centered on the black hole, with a spectrum set by the final particles. If the dark sector does not annihilate, the spike would be quiet in gamma rays, but it would still tug on stars and gas. Either way, the absence of a sharp glow places limits on how steep a spike can be today in busy centers like our own. Second, stellar dynamics. Stars orbiting very close to a black hole precess and wobble in ways that reveal extra mass outside the event horizon. If there were an unseen extended component, dark or otherwise, right around the hole, the orbits would drift differently than pure black hole gravity predicts. For the nearest case, the center of our galaxy, those orbits now set tight bounds on any extended dark mass in the immediate neighborhood. If a spike exists, it must start farther out or be diluted by past scouring. Third, gravitational waves. When a small compact object spirals into a massive black hole, the wave it sings is a long, delicate chirp. A dark spike would exert drag on the inspiral and shift the phase of that song. Future space-based detectors tuned to these slow dances could hear such a shift and turn it into a measurement of the background density near the hole. That would be a new sense entirely, listening for dark matter with gravity's own ear. Fourth, black hole images. The silhouetted rings we now resolve at the edges of some giant holes tell us the space-time geometry just outside the horizon. Dark matter lives far outside that radius. It barely touches the shape of the silhouette. Still, the position and brightness of surrounding plasma depend on the larger potential. While today's images do not pin down a spike, they complement dynamical and lensing constraints in the inner few light years. Could dark matter itself feed a black hole in any substantial way? If it only nudges through gravity, the answer is mostly no. Dark particles zip through the tiny target of the horizon. Only those on very particular orbits get captured. Over cosmic time, the mass gained that way is small compared with what gas can deliver. If the dark sector self-interacts, capture and drag can rise, and in a few models, a spiky cloud might contribute meaningfully to the early growth of seeds. But even there, gas remains the main course. Dark matter is the table the plate rests on. There is a final twist: adiabatic contraction. Even without a black hole, when baryons sink to the center and build a dense bulge, the halo responds by drawing inward. That response makes the central dark density steeper than it was. Later, bursty feedback can puff it back out. Whether a real galaxy hosts a spike, a cusp, or a core thus depends on a timeline. How fast the black hole grew, how violently the center was stirred. When the bulge condensed, how turbulence ebbed and flowed. Each city on the sky writes its own diary. You can hold the full story with 3 images. First, the scaffold and the kiln. The halo is the scaffold that holds the clay. Gas accumulates, warms, and flows. The central light becomes a kiln. Given shelter and time, a small lump can fire into a giant form before the morning breaks. Second, the sand pile at the drain. Where the drain is opened slowly, sand slides inward and stacks into a steep cone, the spike. Where hands keep stirring, or where 2 drains merge, the cone collapses to a gentle mound. Third, the tuning fork. One tine marks baryons, the other dark matter. Touch only one and the note is thin. Touch both. Halos setting the beat for inflow and central spikes adding a quiet overtone. And you hear the full instrument. So, do halos seed early giants? Yes, indirectly but decisively. They do not become black holes. They make the conditions that let seeds form fast and feed well. Can dark matter pile up near black holes? Sometimes, briefly or in quiet places where growth is slow and mergers rare. Often the spike is eroded by the very events that build galaxies. Gas writes the bold strokes of black hole growth. Dark matter frames the canvas and, in favored corners, etches a faint, sharp line close to the center. One that future ears and eyes may yet learn to read. Candidates in one view. WIMPs, Axions, sterile neutrinos. Why machos largely failed. Imagine you're standing at a table of keys. Each key is a different idea for the invisible mass that holds galaxies together. Some are heavy, some are delicate. Some look familiar at first, and then turn strange in your hand. You try them one by one in the same lock, the sky's behavior. Some keys fit better than others. A few turn part way. Most don't turn at all. This is a tour of the best ideas so far, and a clear look at one class that mostly didn't fit. Begin with the workhorse, WIMPs, weakly interacting massive particles. The name describes a personality more than a face. If they exist, they're massive enough to sit still in a halo, rare in their interactions with ordinary matter and honest with gravity. They would have been made in the early universe in just the right amounts if they carry the same kind of weak feebleness that already lives in particle physics. To hunt them, we built quiet rooms deep underground and filled them with ultra-pure targets, often liquid xenon held at the calm of a moonlit lake. The idea is simple. Wait for a rare tap as a WIMP bumps a nucleus, then read the tiny whisper of light and charge. Years of listening have taught us 2 things at once. First, these instruments now hear almost everything, but not the telltale WIMP tap. Second, that no is precise. The newest generations, big twin-phase xenon detectors and their cousins, have set world-leading limits across wide mass ranges. The lock didn't turn, but we learned exactly how it didn't. That matters. It trims the field, pushes us toward new mass ranges, and challenges theorists to sharpen what weakly interacting might really mean. Agenda, indico. +2 agenda, indico. +2 shift to a quieter key, with a very different story. Axions. They were born as a fix for a puzzling symmetry in the strong force, long before anyone thought they might be the dark. If the universe chose this fix, the axion would be feather light and common, filling halos like a cold, almost still field, rather than a gas of individual marbles. How do you listen for something that faint? You bring the right instrument, resonant haloscopes that sit in strong magnets and tune like radios, searching for a whisper of axion, turning into a photon at just the right frequency. Patient scans have now probed important theoretical benchmarks, and the next helioscopes, big magnets pointed at the sun, aim to open territory no one has reached. The key hasn't turned yet, but the teeth are finally precise enough to test the lock head-on. arxiv.org+2 link.ap.org+2 now lift the subtle, in-between key, sterile neutrinos. Regular neutrinos are ghostly but familiar, born in stars and nuclear reactions, passing through matter almost untouched. A sterile cousin would be even quieter. It wouldn't feel the usual forces, only gravity, and a faint mixing with the known neutrinos. If such a particle were a few keV in mass, it could slowly decay, releasing a tiny X-ray photon we might glimpse from clusters or galaxies. For a time, a faint line near 3.5 keV stirred excitement. Then came careful rechecks with wider samples and stricter controls. The signal wavered. The case softened. This key still sits on the table. Some versions remain possible, but the once sharp notch has worn down under scrutiny. Science +2 inspire hep.net +2 turn to a class that once seemed comfortingly familiar. Machos, massive compact halo objects. The pitch was simple. Maybe the halo is just made of ordinary dark things we already understand. Dim stars, brown dwarfs, dead remnants, or black holes drifting through. If so, they would occasionally pass in front of background stars and briefly brighten them by bending light. A microlensing wink we can count. Decades of sky watching delivered a clear verdict. Some such objects exist, but not in the numbers needed. The halo is not mainly built from this family. The key jiggles in the lock and stops. Arxiv.org+1. There is a modern footnote here. Black holes that formed in the early universe, primordial rather than stellar, have been discussed as a special branch of macho-like candidates. Gravitational wave discoveries revived curiosity, and a few narrow mass windows still draw study. But the combined limits from microlensing surveys, the cosmic microwave background, wide-field lensing, and galaxy dynamics leave little room for primordial black holes to make up all of the dark matter. A small fraction in some mass ranges is still on the table. The whole pie, no. Ander.org plows. When you step back, the table of keys tells a practical story about how science moves. WIMP rooms grew larger and purer, ruling out bold swathes of territory and edging toward the neutrino fog, where the very success of observing the universe becomes the next background to overcome. Axion searches tuned deeper and colder, moving from, could we hear anything, to we can now hear the specific whispers theory promised. Sterile neutrino hints were tested like any good rumor, with more data, different instruments, and a willingness to let a beautiful idea fade if the evidence doesn't hold. Machos were given a fair, years-long hearing and then mostly set aside. You don't need to memorize the full catalogue to hold the heart of it. WIMPs. Heavy, shy, still unseen where we first expected. So we push lighter and heavier, simpler and more creative models, and instruments that can live inside the universe's own neutrino murmur. Agenda, indico, axions, featherlight, now reached by radios in magnets and soon by purpose-built helioscopes. The dial is finally sweeping the right stations. Arxiv.org pumps 1. Sterile neutrinos, a graceful maybe, narrowed by careful X-ray work. The loudest early hint is much quieter now. Inspire Hep, net macos. Familiar objects that simply aren't numerous enough. Primordial black holes remain a small, contested corner, not the main story. Anda.org. There's a softer reflection tucked into all this. A good search is an act of listening as much as looking. You make the room quieter. You tune the dial finer. You ask the same question in different languages. Light, heat, timing, gravity. And you let the answers converge or disagree. The convergence is the point. Rotation curves, lensing maps, cluster collisions, the baby picture of the sky and the web of structure all lean the same way. The invisible majority is real. These candidates are our best attempts to name it. So the tour ends where the work begins. With instruments humming in the dark, scanning mass ranges we couldn't reach 10 years ago, cross-checking claims with rival telescopes, and drawing clean lines through yesterday's uncertainties. Some keys have been set back on the table, some are still in the lock, and the universe, patient as ever, will tell us which one turns. Baby picture clues. The peak pattern in the microwave background demands dark matter. Begin at the oldest light we can see, a soft glow that fills the whole sky in every direction, stretched by time into microwaves. This is the cosmic microwave background, the universe's baby picture. Light released when the cosmos was only a few 100,000 years old. Before that moment, space was a bright fog. Matter and light were tangled together, bumping and jostling so often that nothing could travel far without being scattered. Then the fog cooled. Atoms formed, light slipped free and started its long journey to us. What it carried was a memory. A faint pattern of warmer and cooler specks, tiny ripples in temperature across the sky. Those ripples aren't random freckles. They line up into a specific rhythm, peaks and valleys in the sizes of the hot and cold spots. Imagine tapping the surface of a drum and capturing a snapshot of its vibrations. Some notes are loud, some are softer, and their pattern tells you about the drum's shape and tension. The microwave background is like that snapshot. The early universe rang like a drum, really a hot, glowing ocean where gravity pulled matter inward and light pushed outward. The balance between pull and push set up waves, compressions and rarefactions, squeeze and release, over and over, across many scales. When the fog cleared and light went free, we froze those waves in place. Today, when we measure the sky carefully, we find that some sizes of ripples are more common than others. That preference shows up as a peak pattern. You can think of it as a bar chart of which notes were loudest at the moment the music paused. The heights of those peaks and the spaces between them are not just pretty, they carry the recipe of the young universe. Here is the heart of it. That recipe demands dark matter. Why? Because the waves that made the pattern were not happening in emptiness. They were happening in a medium made of ordinary matter tied to light, plus a quieter component, dark matter, that hardly spoke to light at all. The ordinary part behaved like a springy fluid. It could be compressed by gravity and then pushed back by radiation pressure. The dark part did something simpler and crucial. It provided steady wells of gravity that did not bounce with the light, while the bright fluid was busy oscillating, squeeze, release. The dark matter sat there as a calm scaffold, deepening the wells and guiding where the waves would peak. Take a simple image. Picture a row of swings at a playground on a windy day. The wind pushes, gravity pulls, the swings move in time. Now add heavy anchors in the ground beneath some swings. Weights you cannot see that make the low point of those swings a little deeper. The anchored swings will reach stronger, more stable peaks at just the right points in the rhythm. In the early universe, dark matter was the hidden anchors. Without those anchors, the music would have a different shape. The loudness of the notes, the heights of the peaks, would not match what we actually see. Another way to feel it: ordinary matter talks to light, so it sloshes. Dark matter does not. so it does the holding. Because of that, certain peaks in the pattern, the ones that represent places where the fluid was most compressed, come out taller than they would in a universe of light and gas alone. Other peaks, the ones tied to the release phase, are shaped by the balance between the two components. The full set of peak heights becomes a code. Read the code and it tells you how much ordinary matter there was, how much dark matter there had to be, and how the two work together to write the sky. If you set dark matter to 0 and try to replay the song, you run into two problems at once. First, the peak pattern comes out wrong. The notes don't have the right loudness relative to each other. Second, even if you tried to force a fit, the universe later would grow its cosmic web too slowly. The bright fluid's constant tug-of-war with light would keep smearing out the seeds of structure. Galaxies would struggle to form on time. With dark matter, the seeds are planted early and deep. After the fog lifts, the bright matter can fall into those quiet wells and build the filaments and clusters we map today. Think about the timeline. In the beginning, everything was hot, dense, and glowing. Tiny differences in density, small wrinkles were present. Gravity tried to pull the wrinkles tighter. Light, trapped with ordinary matter, pushed back like a spring. The result was a set of sound-like waves rippling through the young universe. Then, at the moment the fog thinned and light decoupled from matter, we caught a freeze frame of those waves. That is the microwave background, a photograph of the universe mid-ring. From that photograph, we can do more than admire. We can measure. We measure the typical sizes of warm and cool spots across the sky. We see a first favored size, then a second, then a third, like finding the fundamental note and overtones of a musical instrument. We compare their relative strengths. The comparison is the giveaway. It says the instrument that played this song had a bright, springy string and a dark, steady frame. There are extra details in the baby picture that deepen the story. Very small ripples are partly blurred away by the last bit of scattering, like ink that smudges at the edges, giving a gentle fade toward the smallest scales. The light is also polarized in a particular pattern, a subtle swirled alignment that adds another set of clues about how the early waves moved. And as that ancient light travels to us, the large-scale structure it passes through, galaxies, clusters, and the wide web, slightly deflects it, imprinting a faint, graceful distortion. Even that distortion, when mapped, agrees with a universe where dark matter is the main scaffolding. You do not need the mathematics to accept the logic. You need the picture. The peak pattern is a memory of a duet. Radiation pushing out, gravity pulling in. Ordinary matter sang both parts because it felt both the push and the pull. Dark matter sang only the low, steady note of gravity. Without that low note, the chorus of peaks would be off-key. With it, everything lines up. The baby picture's rhythm, the later growth of the cosmic web, the way galaxies rotate, and the shapes carved by lensing across the sky. If names help you anchor the idea, you can whisper a few. Early satellites first detected the smooth glow. Later missions sharpened the freckles into a precise map. Each generation tightened the error bars, and the same answer kept returning. A small slice of ordinary matter, a larger slice of dark matter, and a broad backdrop of something that drives expansion on the biggest scales. Different instruments, same melody. Hold three simple metaphors for narration. First, the drum. The early universe is the drumhead. Gravity and light are the forces that make it ring. The captured peaks are the loud notes. Dark matter is the heavy rim that keeps the drum in tune. Second, the soup. The young universe is a bright broth. Stir it and it sloshes. Drop in invisible stones, dark matter, and the soup now swirls around stable centers. When you freeze the pot, the swirl pattern tells you the stones are there. Third, the choir. Some voices sing high and tremble. Some voices sing low and steady. The peaks we observe require both. The low voice is the unseen mass. What does this chapter add to your larger story? It closes a loop. You've heard from galaxies that spin too steadily to be held by light alone. You've watched clusters weigh more than their glow implies. You've seen light bent into arcs and rings by halos that outgrow the visible. You've traced a web in tiny shears where mass spreads beyond the stars. Now the universe's oldest light, its first clear portrait, confirms the same truth from the opposite end of time. The baby picture and the grown-up structure agree about the quiet majority. So when you hear the cosmic microwave background demands dark matter, translated into something human and clear, the oldest light remembers a rhythm that only a hidden, steady weight could have set. The peaks are not decorations. They are evidence, and they point to a universe where the bright, familiar 5% sings upon a deeper, quieter stage. The stage that holds the melody together from the first note to the one you're hearing now. Colliders and missing energy make dark matter at the LHC, mono-X events, and the limits we've learned. You walk from quiet rooms under mountains to a different kind of listening, a cathedral of magnets and steel where protons collide near light speed. Beams cross tens of millions of times per second. From those crossings, fragments bloom like fireworks inside building-sized detectors. The question is simple and audacious. If the universe is full of invisible matter, can we make a little of it here? A collider's advantage is directness. Instead of waiting for a rare bump or a faint glow, you smash ordinary particles so hard that, if a heavy, quiet partner exists, it could be born in the wreckage. The challenge? If you succeed, your prize refuses to talk. A dark particle ghosts through the detector. No tracks, no sparks, no shine. So colliders hunt by what is missing. The visible debris is measured with care. Momentum and energy of every jet, flash, and muon. In the plane perpendicular to the beams, momentum should balance. Push left equals push right. When it doesn't, when the event looks like a table with one leg gone, you whisper, met, missing transverse energy. That imbalance hints that something invisible left the scene carrying momentum. But simple stories are rare. Neutrinos also vanish. Detector edges hide things. Many mini-collisions pile up, confuse the picture. The art is to sculpt chaos into clean categories, teaching the machine when missing matters and when it's a mirage. Enter mono-X hunts, mono-jet, mono-photon, mono-Z, mono-W, even mono-Higgs. If two invisible particles are created, you won't see them, but sometimes a single visible object recoils. A hard jet, a bright photon, a heavy boson. That one object is X. You trigger on X, measure its punch, then look for a big, clean slab of emet opposite, as if two invisible runners sprinted away together. Monojet is the workhorse. A high-energy jet slams in. Nothing comparable balances it. Main backgrounds, Z plus jet where Z, neutrinos, W plus jet where W, lepton plus neutrino, but the lepton is missed. And multi-jets where mismeasurements fake emet. Analysts corral these with control regions, events where Z, two leptons, or where the W's lepton is found on purpose. Tune to those honest samples, then predict how many invisible Z and lost lepton W events spill into the signal region. If data still rise above the discipline prediction, you lean forward. Monophoton is similar but cleaner to trigger and model. Mono-ZW asks for a reconstructed boson, LA for Z, else met for W, recoiling against more met than the boson explains. Mono-Higgs is rarer but special. If the Higgs couples to the dark sector, it could be produced with, or decay into, invisible partners. Its visible decay then balances too much met to ignore. Every channel needs calibrators, jet energy scales and tails, spotless photon ID, crisp lepton triggers, and met itself, measured with multiple algorithms and cross-checked. What would make searches light up? A steady excess at high met, with shapes across channels that agree, and with jet counts and angles matching a simple story. Pair production of invisible particles via a new mediator that also radiates X. Not a single firework, but a pattern that hardens with more data. That mediator matters. A point-like contact handshake is a handy cartoon, but at LHC scales there may be a real particle in the middle. Is it photon-like or Higgs-like? Does it prefer quarks or leptons? Is it light enough to appear on shell and decay invisibly? Or back to standard particles as a resonance? Hence simplified models. Keep the cast small, dark particle plus mediator, and scan masses and couplings. If the mediator is light and talks to quarks, DJ spectrum may show a bump. If it prefers leptons, watch the leptons. If it mixes with the Higgs, invisible Higgs decays and VBF plus MET grow sensitive. The lesson: complementarity. Any viable story must pass several gates, not just mono X. What have we learned? No channel has produced a clean sustained excess. That absence draws contours. If dark matter is light enough to produce and couples with a given strength, that strength must be weaker than this. If the mediator sits in a certain mass band and talks a certain way, it must do so more softly than that. These are boundaries, not defeats. They shepherd theory toward quieter couplings, heavier or subtler mediators, lepton-leaning portals, or richer sectors. Those boundaries cross-talk with underground rooms and the sky. If the LHC squeezes a mediator, direct detection looks elsewhere. If gamma rays hint at a scale, collider teams check whether a matching mediator is ruled out or discoverable with mono-X or resonance hunts. 3 maps: collider, direct, indirect, enable triangulation. The overlap carves out islands where all 3 agree. Colliders probe corners underground, finds awkward. If the dark particle couples to leptons, heavy nucleus targets are less sensitive, but monolepton plus MET is at home. If the sector is compressed, mono-X plus soft stuff and disappearing track shelp. If a light, long-lived mediator drifts before decaying, downstream detectors can catch it. Not dark matter itself, but the portal that links worlds. Respect the honest mess. Pile-up layers peeled like onions. Jet scales tuned to fractions of a percent. MET tails modeled with care. Backgrounds checked in orthogonal regions and inverted selections. Any excess must survive stability tests. Shift cuts. Swap algorithms. Split by time and detector quadrant. And keep its shape. A human picture. You're in a windy field with confetti. Pile up, debris. 2 invisible runners tear past. You notice because one hat, jet photon Z, flies off one way, and the tug on your coat, Emmet, is big the other way. Months taught you how often hats fly off for mundane reasons, and how the wind tugs when no one is there. Now you count the rare moments when both happen together. Just so. More often than your careful book allows. Limits aren't defeat. They're progress reports. They say the tidy versions are too loud. If true, they must speak more softly or from a new angle. Some limits press on the classic thermal relic benchmark. That pressure reshapes ideas. Maybe the mediator favors the second generation, sits in a trigger-awkward window, or speaks in a scalar whisper rather than a vector shout. Discovery would be a weave, a monojet excess at high MET growing with data and showing the right angular patterns. A matching hint in monophoton at the same scale, no digit bump if the mediator avoids quarks, or a modest one where expected if not. A small, aligned increase in ZEPSMET. No contradictions in clean controls. Fit together. One narrow band of mediator and dark particle masses explains all curves. Then carry that band to underground and sky. Does it fit recoil data and the lack of a gamma glow? If yes more than no, you're close. Carry 3 images. The balance scale. Lay every visible grain on one pan. The scale should sit level. When it tilts hard with nothing opposite, ask who stepped off. The recoil snapshot. 2 invisible swimmers dive. A single splash arcs the other way. From the splash and ripples, you tell something dove. The map of islands. Direct searches shade oceans. Indirect searches shade others. Colliders shade a third. Where all 3 leave land, that's where discovery likely stands. So when you hear colliders and missing energy, mono-X and limits, keep it human. We try to make the unseen, then recognize it by the hole it leaves and the single object that recoils. We haven't caught it yet, but with smarter triggers, cleaner calibrations, and deeper runs, the simple stories are trimmed, the islands shrink to where truth can live, and the day draws closer when a missing line in a ledger will be enough to rewrite the cast list of the universe. Cosmic web and simulations. Lambda CDM grows filaments, halos, and clusters that match surveys. Begin with a quiet universe in your mind. Not empty, just even. A smooth sea with tiny wrinkles. Those first wrinkles are the seeds left by the early cosmos. The faint memory the baby picture of the sky preserves. Now let time run. Gravity tugs on each slightly denser patch. The quiet matter that doesn't shine gathers first, deepening shallow dents into wells. Ordinary matter follows, cooling and condensing where those wells are strongest. This steady choreography is the backbone of our best working recipe. A gentle global push we call dark energy. A calm clumping scaffold we call cold dark matter. Together, they form the simple framework often nicknamed Lambda CDM. To watch this story unfold, we grow it in a computer. We carve out a big cube of the universe, sprinkle it with tracer particles that stand in for mass, and set their starting positions and motions to match the pattern of early wrinkles. Then we press go. Step by patient step, gravity pulls particles together. Threads appear. Knots bloom where threads cross. Little knots merge into bigger knots. What emerges is a web. Long filaments, rounded halos, and sprawling clusters spread across a vast foam of empty rooms we call voids. Look closely at this simulated web. Filaments are highways between cities. Halos sit at the interchanges, deep, rounded wells where galaxies can live. The larger cities are clusters, where many halos are bound together, surrounded by rivers of infalling matter. Between them stretch wide, quiet voids, places where gravity has gently evacuated the stage. It isn't a random tangle. It's a pattern with grammar, written by gravity acting over time on slow, cold, dark matter, while the background expansion sets the tempo. Now hold this web beside the maps we draw from real telescopes. When wide surveys chart millions of galaxies, the same foam-like structure appears. Bright chains of galaxies along luminous filaments, dense knots where clusters sit, and cavernous spaces with only a few dim beacons. When we weigh the sky with the tiny stretches of weak lensing, the mass arranges itself in a matching network, often wider than the light, but tracing the same roads and crossings. Simulations and surveys speak the same language, down to startling detail. Why does the match come out so well? First, cold dark matter clumps early and on many scales. Because it doesn't glow or collide like gas, it builds structure efficiently. Small halos form quickly, then merge to build bigger halos. That cascade creates a natural hierarchy. Satellites inside hosts, hosts inside groups, groups inside clusters, clusters strung along filaments. The fine grain you see in simulations becomes the swarm of satellite galaxies and substructure we search for in the real sky. Second, dark energy is gentle but steady. It doesn't tear apart structures that are already bound, but it slows the birth of new giants on the largest scales. In simulations, this slow push lets the web form early and then stretch. Nearby space looks like a matured network, while the far, young universe looks smoother and less clumpy. Deep surveys that peer back in time confirm the same age gradient. The web thickens with cosmic years. Third, the initial wrinkles matter. We tune the starting pattern using the sky's baby picture. Simulations grown from those seeds reproduce the typical spacings and sizes we measure today. You can think of it like planting a field with a specific distribution of seeds, and then watching the same rows and clusters of growth appear where you expect them. There's a fourth reason. 2. We compare like with like. Modern runs don't just spit out particles. They produce mock skies. We cast virtual light cones through the simulated universe, the same kind of geometry observers see, and then apply the same selection rules real surveys use. If a telescope would miss dim galaxies, the mock misses them too. If atmosphere blurs shapes, the mock blurs them as well. When we measure both the mock and the real sky with the same ruler, the agreement becomes meaningful. Of course, the luminous parts have weather of their own. Ordinary matter can cool into clouds, ignite into stars, explode as supernovae, and drive winds. Black holes at galaxy centers can heat and stir their surroundings. These processes sharpen or soften what we see. To paint those bright details on the dark scaffold, modern simulations add feedback that captures the broad effect of stars and black holes on gas, even as those details shift the glow. Thicker cores here, thinner disks there. The large-scale web endures. The statistics of the simulated universe keep echoing the real one. How do we judge the echo? We count halos by size and compare with the number of galaxies and clusters we find. We measure how galaxies cluster across different distances and check whether simulations show the same scale-by-scale rhythm. We read weak lensing maps and ask if the simulated mass fields create the same delicate shears. We link galaxy light to the mass of their halos using several cross-checks, lensing for the outskirts, satellite motions for the inner regions. Again and again, the lambda CDM backbone holds. There are nuances and puzzles that keep the work honest. How dense are the smallest halos? How many tiny companions should orbit a Milky Way-like galaxy? How strongly do black hole winds change how gas settles into stars? Simulations and surveys meet in these details and argue kindly until the numbers align. Sometimes we refine the physics of star formation. Sometimes we refine how we connect galaxies to halos. The frame stays the same, a quiet scaffold of cold, dark matter shaped by a gentle cosmic push. Simulations let us zoom as well as pan. Start with a large box to capture the broad web, then zoom in on one patch with finer resolution, a city block inside the continent. In those zooms, we watch single halos grow, see streams of material spiraling in, and resolve the dance of satellites as they're tugged and tidally shredded. We learn how thin disks survive mergers, how thick stellar halos form from past encounters, and how gas rains back after being blown out by stellar winds. These close-ups teach us which bright features of galaxies trace their dark histories. Simulations also let us run what-if worlds. What if the quiet matter was slightly warmer and smeared out the smallest clumps? What if it bumped into itself a little and softened halo cores? We grow those alternative webs and compare them with the sky. Too smooth, and we lose the satellite population we observe. Too sticky, and we blur strong lensing signals that demand dense substructure. In this way, the real web trims the family of allowed possibilities, tuning the personality of the unseen. The web connects with another clean ruler, a faint, preferred spacing in the galaxy distribution, like ripples that froze long ago in the young universe's bright broth. Simulations seeded with that early memory grow galaxy maps where the same gentle ripple appears. Surveys measure it. The distances it encodes confirm the pace of expansion that the rest of the model assumes. Separate clues, same answer. If you like simple images, keep these close. Bread dough with raisins. The universe is the dough. The overall rise is expansion. The raisins are halos. As the dough rises, gravity draws raisins together in places, building clusters along faint strands. The rise and the clumping happen at once, a road atlas at night. Highways are filaments, interchanges are clusters, towns are halos. Even if you dim the streetlights and only feel the pavement under your feet, the road layout stays the same. Frost on a window. Branching lines grow and meet, forming thicker nodes where lines cross. That branching is how the cosmic web builds, small lines becoming larger structures as they merge. There are practical gifts too. By matching simulated skies to real ones, we can turn complex observations into clean inferences. How massive is a cluster whose weak lensing signal looks like this? Check the mock catalogs. How many satellites should a galaxy of this brightness host? Read the distribution from the zoom runs. How far does a typical halo extend beyond a galaxy's light? Stack the simulated profiles and compare with lensing measurements. The web turns from picture to measuring tool. All of this folds back into a soft reflection. The web shows how complexity blooms from simple, patient rules. Start with small differences. Add time and a steady pull. The result is not chaos but form. Threads, knots, rivers of matter, and homes for stars. Your life knows the same rule. Small habits repeated become the scaffold that holds bigger plans. So when you hear cosmic web in simulations, lambda CDM grows filaments, halos, and clusters that match surveys. Translate it into something clear and human. We plant the universe's earliest memory into a digital sandbox. Let gravity and expansion do their quiet work, and a web appears that looks like the real sky. The match is not luck. It is a sign that the recipe captures the main ingredients. The quiet scaffold of cold, dark matter shapes where things form. The gentle push of dark energy sets the pace. Ordinary matter lights the stage, and with each deeper survey and sharper simulation, the sketch becomes a portrait. The same roads, the same cities, the same wide, dark countryside, drawn by gravity's patient hand and illuminated here and there by stars. Direct detection underground. You ride an elevator into quiet. Rock closes around you, layer after layer, until the chatter of cosmic rays is mostly gone. Down here, experiments listen for a footstep so soft it would be lost above. The hope is simple and brave, that a passing dark matter particle will bump a single nucleus, nudge it by a hair's breadth, and leave a whisper you can record. That nudge is a nuclear recoil. The underground halls are built to hear it. Why underground at all? Because the sky rains noise. Fast particles from space seed false signals. Stone shields. Add water tanks, plastic walls, lead. The room grows quieter. Place veto layers around the detector's heart to tag intruders. Learn the sense of common radioisotopes and scrub them away. You do all this because the thing you want is so rare that even a few stray clicks can drown it. 3 broad approaches share the stage. Big baths of noble liquids and cold crystals that feel the faintest heat. Each listens for the same event, a nucleus kicked by an invisible visitor, but translates the whisper differently. Start with liquid xenon, a noble element that glows when disturbed. Imagine a tall, clear vat of xenon chilled to a calm liquid with a thin layer of gas on top. When a particle bumps a xenon nucleus, 2 things happen. First, a tiny flash appears. Second, a handful of electrons are knocked loose. An electric field lifts those electrons upward. In the gas, they make a second longer flash. 2 flashes, one then another, form the signature. The time between them gives the depth. The light pattern above and below gives the sideways position. Put them together, and you know not only that something happened, but where. Location is power. Xenon is heavy and self-shielding, so outside layers soak up lingering radioactivity. By keeping only events from deep inside, the fiducial volume, you push away most backgrounds without touching potential signal. Xenon also helps you tell what happened. Backgrounds often jostle electrons. Dark matter should jostle nuclei. The ratio between the flashes, plus how spread out the second is, separates electron events from nuclear recoils. You draw a clean region in this space and listen there. Keeping xenon pure is its own art. Trace gases can glow or mimic signals. Certain isotopes imitate what you seek. Teams distill and recirculate, peel away unwanted guests, atom by atom, and test air and materials with near meditative patience. They lower detectors into pools of ultra-pure water that shield and also catch cosmic stragglers. Then they wait, sometimes for years, counting only events that pass every filter and geometric cut. Shift to liquid argon, a cousin with a different gift. Argon glows too, but the glow has 2 flavors, a quick component and a slow one. Electrons and nuclei excite these in different proportions. Look at the shape of a flash and ask, was this electron-like or a nuclear recoil? That pulse-shaped discrimination is argon's superpower. It offers another way to discard common backgrounds. Argon's challenge is a faint atmospheric radioisotope that sprinkles the liquid with unwanted clicks. The solution is literal. Draw argon from underground pockets where that isotope never formed, and the noise drops. The inner walls wear a thin coat that shifts ultraviolet light to a color sensors love. The geometry stays simple and clean. Selection is strict. The result is a detector that can sit quietly for long stretches, hunting the same single scatters as xenon, but with a different accent in how it says no. Now move to the crystals, where listening changes from glow to heat. Imagine a disk of germanium or silicon chilled so close to stillness that even the tiniest kick warms it perceptibly. A dark matter recoil sends a ripple through the lattice, vibrations that carry energy to sensors perched like stethoscopes on the surface. Many setups also collect the faint charge from the same event. Heat and charge together form a fingerprint. Electron events tend to make more charge for a given heat. Nuclear recoils make less. Plot one against the other and two clouds peel apart. The nuclear cloud is where you dwell. Some crystal experiments add a third whisper, light, by using scintillating materials that glow when hit. Heat, charge, and light form a triple handshake that narrows backgrounds further. Crystals usually carry less mass than big vats, so they listen to fewer atoms at once. But they listen exquisitely well. Thresholds can be astonishingly low, reaching into regimes where light-dark matter would leave only the faintest footprints. In the same underground silence, different instruments tend different gardens. In all approaches, neutrons are the trickiest background. Neutrons bump nuclei just like dark matter. They sneak through shields that stop most other radiation. To tame them, teams add hydrogen-rich layers to slow them, surround detectors with water or plastic, and sometimes lace that water with capture agents that flash when a neutron is swallowed. Geometry helps too. A neutron is more likely to collide more than once. Dark matter should hit just once and be gone. Multi-scatter events are almost always thrown out. How do you know you can hear what you claim? You calibrate. Introduce known sources that cause nuclear recoils and measure how they look. Leak in a trace isotope to tag depth and alignment. Flick tiny light pulses through the liquid to check timing. Aim a well-understood neutron beam during commissioning to map response. Blind the most interesting data while you finalize cuts, so choices cannot lean toward a desired answer. Only when rules are fixed do you open the box, count the survivors, and let statistics speak. It is nearly poetic how much of this work is the subtraction of everything else. You remove radioactivity from steel and cables, swap sensors until their own glow is negligible. Learn the breath of radon and keep it out. Pick rocks with the cleanest history to line the lab. The instruments become less like machines and more like rooms for listening. What do you expect if the dark matter plays along? Not a firework. You expect a few events in the right place on your maps, with energies and shapes that match nuclear recoils and positions deep in the safest volume. They should be unclustered in time, show no kinship with neighbors, persist when you vary cuts sensibly. They should stand where background models predict almost none should stand. That is the picture you carry into every unblinding. There is a horizon to this race, with a lyrical name, the neutrino fog. The universe itself makes ghostly particles that can bump nuclei and produce the same signal you seek. Solar, atmospheric, and ancient supernova neutrinos will, at some point, fill your clean box with a background no shield can block. Reaching that horizon is not failure. It is a milestone. It means you have quieted every earthly whisper so well that only the universe's murmur remains. Beyond it, progress comes from sharper pattern recognition, new targets, and clever tags that tease apart the slight differences between those ghosts and dark matter. Along the way, diversity matters. Xenon, argon, germanium, silicon, and scintillating crystals do not just compete. They cross-check. If a hint appears in one, you look for a matching hint in another, in a mass range where both are sensitive. The way a signal scales between heavy and light targets is a tell that backgrounds cannot fake. Different strategies for rejecting electrons and neutrons make shared false positives unlikely. A real discovery would rhyme across materials and methods, not solo in a single hall. There is also a time rhythm some experiments watch. As Earth orbits the Sun and the Sun moves through the galaxy, our speed through the halo changes slightly over the year. If the signal is real, the rate could modulate gently with the seasons. A clean annual sway, in phase and amplitude with expectations, would be a compelling chorus member, not proof by itself, but a hard song for backgrounds to sing. What does this add to your larger story? It ties the grand to the tactile. You have watched dark matter shape galaxies and bend light. Here you feel the hope of catching a single touch on a single atom. You have heard how freeze-out could leave fossils, how Axion waves might smooth small structures, how warm and self-interacting variants tweak local texture. Here you see the listening rooms built to test those ideas directly, one quiet recoil at a time. Carry 3 images as you leave the underground. First, a lantern in a cave. The cave is the detector. The walls are scrubbed clean. A dust mote bumps the glass. The slightest flicker, and the watchers mark it down. Second, a lake at night. 2 pebbles thrown one after the other make 2 ripples. The time between ripples tells depth. The shape tells what threw them. That is the language of noble liquids. Third, a bell in winter air. Touched lightly, it still sings. The colder the air, the more clearly you hear the strike. That is the crystal's craft. So when you hear direct detection underground, translate it into something clear and human. Clean rooms under mountains. Noble liquids glowing twice to reveal where and what. Crystals shivering with tiny heat. And a patient search for the rarest tap. The work is meticulous, the pace deliberate, and the reward, if it comes, will be a small, undeniable whisper that changes the map of everything. Einstein rings and arc-strong lensing that maps dense clumps of dark matter begin with a simple picture. A distant galaxy glows like a candle at the far end of the universe. Between that candle and us sits a massive foreground object, a heavy galaxy with a dense heart, or a whole cluster crowded with smaller galaxies. That foreground mass doesn't block the light. It reshapes the space the light must cross. When the alignment of candle, lens, and observer is close to perfect, the background galaxy is stretched into a smooth circle wrapped around the lens. That circle is an Einstein ring. When the alignment is a little off, the circle breaks into crescents, bright arcs, mirrored smudges, multiple copies of the same distant source arranged around the lens like beads on an invisible string. These rings and arcs are the bold-faced letters of gravity. They say, clearly and loudly, there is a lot of mass right here, and because light responds to all mass, whether it shines or stays quiet, these shapes let us weigh what we can't see, especially dark matter. Think of the foreground mass as a crafted piece of glass. If the glass were perfectly smooth and centered, the ring would be smooth and centered too. But if the glass has slight ripples or hidden bumps, small clumps tucked inside the larger lens, then the ring kinks, the arcs thicken in places, or an extra tiny image appears where none should. Those imperfections in the ring are clues. They tell you about substructure, dense pockets of matter, many of them likely made of dark matter, hiding within the larger halo. In this way, strong lensing becomes a microscope for the invisible landscape inside galaxies and clusters. Let's walk through a few classic scenes to make this concrete. Scene 1. A single massive galaxy acts as the lens. The background source might be another galaxy or a flickering quasar. You look at the image and see 2, 4, or even more copies of the same distant object, placed around the lens in a symmetric pattern. If the alignment tightens, those copies blend into an almost complete ring. The precise locations and brightnesses of those copies pin down the lens's mass, how concentrated its center is, how stretched its halo is, and whether small dense knots are lurking near the light paths. With careful modeling, that single system becomes a scale that weighs the lens to remarkable precision. Scene 2. A cluster acts as the lens. Now the stage is busy. You see long, delicate arcs wrapping around the cluster's crowded core. Some arcs are thin and ribbon-like, others are thick and bright. In the best cases, you can identify multiple images of the same background galaxy scattered in a graceful curve. By tracing these arcs, astronomers draw a mass map that often extends far beyond the region where the cluster shines. Where an arc twists or splits in a surprising way, you often find a subhalo, an especially dense patch, likely dominated by dark matter, tugging at the light like a hidden hand. Scene 3. A lensed quasar. The same flickering beacon appears in multiple places around the lens. Because the different copies take different routes through differently curved space, they arrive at slightly different times. The quasar brightens, and then one copy responds, then another, each with its own delay. Those delays become a clock. Combined with the geometry, they let us cross-check the mass model and even refine our measurements of cosmic distances and the expansion rate of the universe. In a single graceful system, strong lensing becomes both a scale and a clock. Beyond these set pieces, strong lensing gives us something priceless: magnification. A very distant small galaxy that would be just a faint smudge can be enlarged and brightened by a foreground lens, revealing star-forming clumps and structure that would otherwise be hidden. It's as if the universe lends you a natural telescope made from gravity itself. With it, we study some of the earliest galaxies, peering back toward cosmic dawn. The lens both teaches us about the foreground mass and gives us a clearer view of the background universe. Why do rings and arcs matter so much for dark matter? Because they are exquisitely sensitive to clumpiness. Many ideas about dark matter predict a hierarchy: big halos holding galaxies and clusters, and inside them a swarm of smaller subhalos, little seeds nested within the fruit. Stars and gas alone cannot produce the expected crowd of seeds, but arcs feel them. A subhalo near a light path can tug an arc sideways, fatten part of it, or create a faint extra image. By measuring these nudges across many lenses, we learn whether dark matter is arranged the way our best models expect, how dense those subhalos are, and how common they might be. This is not a thought experiment. It's a direct test of dark matter's personality: quiet and smooth, or quiet and grainy. Strong lensing also helps separate what shines from what holds. Consider two clusters that have collided and are passing through each other. The hot gas, the bright ordinary matter, slams together, slows, and glows between the two swarms. But the lensing map shows most of the mass moving ahead with the galaxies, almost as if the deeper weight passed through the crash with very little fuss. Light suggests one distribution, lensing draws another. The difference is the signature of a dominant unlit component. To use strong lensing well, you need the right geometry: a background source, a massive lens, and our viewpoint aligned just so. You also need sharp images, because tiny features carry big meaning. That is why some of the most beautiful and scientifically rich pictures from space telescopes show clusters wrapped in blue or red arcs, curves that are more than decoration. Each curve is a measuring tape laid on the sky. Here are a few ways astronomers read those tapes. First, they build a light map, where the stars and gas are in the lens. Then, they build a lensing map, where the mass must be to produce the observed arcs and rings. By comparing the two, they see where mass and light agree and where mass goes its own way. Agreement is reassuring. Disagreement is revealing. It often points to dark matter spread wider than the light, or gathered into small knots that have no bright counterparts. Second, they look for flux anomalies, places where one copy of the lensed image is brighter or dimmer than a smooth model predicts. Those mismatches can be fingerprints of subhalos messing with the light path. Even when a subhalo is completely dark, it leaves a signature in the brightness pattern. In this way, strong lensing counts invisible clumps. Third, they combine strong lensing, which is sensitive to the inner, high-density regions, with weak lensing, which traces the broader outskirts through very gentle stretches of background galaxies. Together, the two methods paint the mass from the crowded core out to the wide, dim halo, giving a complete portrait. Sharp features at the center, soft structure at the edge. If you prefer simple images to hold in your mind, try these. Imagine chalk lines on a dark board. The ring is a chalk circle drawn by light itself, sketching the shape of the hidden weight. Where the chalk line kinks, a hidden bump sits underneath. Imagine a lake with floating leaves. The leaves trace invisible currents you can't see directly. The arcs are the leaves. Dark matter is the current. Imagine a funhouse mirror that reveals its dents by how it warps your face. You don't need to touch the mirror to find the dents. You study the distortion. Rings and arcs are that study writ across the sky. Strong lensing has limits, of course. Not every alignment produces dramatic features, and modeling can be tricky. But when the scene cooperates, a single ring can weigh a galaxy's core to exquisite precision, and a single gallery of arcs can expose a cluster's hidden skeleton. With each new lens, we test whether dark matter is as cold and clumpy as our leading pictures suggest, or whether it behaves more softly, spreading out in ways that smooth the smallest structures. The arcs themselves are the evidence. There's a wider gift here. Strong lensing connects scales. On the smallest, micro-lensing moments can reveal compact, wandering masses as they briefly brighten a background star or quasar image. On galaxy and cluster scales, rings and arcs map halos and subhalos. On the largest scales, the faint statistical bending of countless distant galaxies traces the cosmic web. Across all of them, the rule holds: light is honest about mass. So when you hear Einstein rings and arcs, think of a precise, generous ruler laid across the sky. Think of a microscope that sees structure without needing the matter to glow. Think of a timepiece that measures delays between mirrored flickers to refine our sense of distance. Above all, think of a quiet conversation between light and gravity, where light tells us exactly how the unseen is arranged. With every new ring we resolve and every arc we model, the hidden architecture of the universe comes into sharper focus. Circles and crescents, sketching where mass pools most deeply, where halos spread, and where small, dense knots of dark matter hide within the larger embrace. The drawings are beautiful. The message is simple. The invisible can be mapped, and the map is written in light. Gravity as a lenshow mass bends light. Lensing as our ruler for invisible stuff settle into the idea that space is not a rigid stage. It has give. Put enough mass in one place, a star, a galaxy, a whole cluster, and the space around it dips and curves. Light, always honest, follows the curve. It doesn't pause to decide. It simply takes the best available path through a landscape your eyes can't see. That is gravitational lensing, mass shaping a road that light must travel. Imagine a candle behind a wine glass. You know the candle is simple, a small flame, yet through the curved glass it smears into arcs and doubles. It brightens, it shifts, it becomes more than one. Nothing happened to the candle. The glass did all the work. In the sky, foreground galaxies and clusters are the glass. Distant galaxies are the candles. Their light pours through curved space, and the distortions become clues to the depth and shape of the curve. Sometimes the effect is gentle. That's weak lensing. The background galaxies are stretched a little, like soft taffy, too subtle to notice one by one, but collect thousands, millions, and their tiny alignments reveal a pattern. With statistics and patience, a mass map appears, a map that includes whatever is there, glowing or not. It's like watching a field of tall grass. One blade tells you almost nothing, but a sea of them shows you the shape of the wind. Other times the effect is dramatic. That's strong lensing. A single distant galaxy can show up as a bright arc, a ring, or several copies scattered around a foreground mass. You can point to them, copy, 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 the same objects seen along different routes. In those scenes, lensing becomes architectural. The angles and separations weigh the lens and reveal where its gravity is strongest. The bent and repeated light turns into a measuring tape for what you can't see. Why is this our ruler for the invisible? Because lensing does not care whether matter shines. Stars, gas, dust, and dark matter, all of them bend light the same way, by simply being there. When we compare a lensing mass map with a map made from light alone, we get two drafts of the same landscape. Often they agree in outline. Often the lensing draft sprawls wider and heavier, exposing the quiet majority that doesn't glow. There's a special kind of scene where the lesson is unmistakable. two galaxy clusters colliding and passing through each other. The hot gas between them slams together and lingers in the middle, glowing in high-energy light. But the lensing map shows most of the mass gliding ahead with the galaxies, as if the deeper weight barely noticed the crash. Light gives one impression. Lensing corrects it. The foreground actors aren't the whole cast. Behind them, the invisible carries most of the story. Think of lensing as a set of tools, each tuned to a different scale. Galaxy-galaxy lensing. Stack the subtle stretch of many background galaxies around many foreground ones. The average pattern outlines halos that are too faint to see directly, revealing how far those halos extend beyond the visible edges. Cluster lensing. Strong arcs and rings act like signposts. Weak, statistical stretches fill in the outskirts. Together they trace the mass from the bright core to the wide, dim halo. Cosmic shear measure tiny alignments across huge swaths of sky. The pattern sketches the great web of structure, its threads, junctions, and empty rooms, without asking the matter to shine. Lensing is also a magnifying glass. Sometimes a distant faint galaxy becomes visible only because a natural lens in front makes it brighter and larger. Gravity lends us a telescope made of space itself. Through it we glimpse very early galaxies, tiny and far, that would otherwise be lost. The lens not only measures the invisible, it lets us see the barely there. It even gives us time. When a distant flare of light takes multiple routes around a foreground mass, its copies arrive at different moments. By timing those arrivals and knowing the geometry, we can refine how fast the universe expands and how large our cosmic rulers truly are. In that sense, lensing is both a scale and a clock. It weighs what we can't see and times what we can't hold. If you like simple images, keep these close. First, the warped window. You don't need to know the recipe of the glass to see its distortions. You watch the view behind it, notice the smears and stretches and infer the curve. That's lensing. Second, footprints in snow. You may not see the walker, but the pattern tells you their weight and stride. Lensing is the imprint left on background light by foreground mass. Third, a city seen through heat ripples. The buildings haven't moved. The air has. The shimmering betrays the unseen currents. In space, the shimmer is geometry, and mass makes the currents. Lensing also connects scales that are hard to join by other methods. On the smaller scales, compact objects like isolated stars or remnants can briefly magnify a background source as they pass in front, an effect called microlensing. It lasts days to months, and it can reveal otherwise hidden companions or wandering masses. On galactic and cluster scales, strong and weak lensing map halos and bridges between galaxies. On the larger scales, delicate patterns in the oldest light are smoothed and shifted by the accumulated bending from all the matter in between, letting us weigh the average pull of the universe. Every tool has limits, and lensing is no exception. It is subtle. It demands careful control of tiny blurs and biases in the images we take. But its strength is stubborn. It reads mass directly through its effect on light. Where measurements from light alone can be fooled by dust or star formation, lensing stays focused on the underlying weight. What does all this say about dark matter? It says that halos around galaxies are not guesses, but mapped shapes. It says that clusters carry broad envelopes of mass that extend far beyond their bright cores. It says that the grand structure of the universe, its threads and crossings, can be drawn without a single photon from the matter that holds it together. The comparison between the lensing map and the light map then becomes a conversation. Where they match, our picture is stable. Where they differ, the quiet scaffolding shows itself. There's a soft philosophy here. In daily life, truth often shows itself by the way it changes other things. You may not see kindness itself, but you see how a room eases when someone kind arrives. You may not see the wind, but you know it by the trees. Lensing is that wisdom at cosmic scale. We don't demand the dark become bright. We let the bright reveal how the dark is arranged. So when you hear gravity as a lens, translate it into something human and clear. Mass reshapes the path of light, and those reshaped paths are clues. By reading them patiently, we weigh the unlit, map the unspoken, and even borrow magnification from the sky itself. With that ruler in hand, we can keep tracing the outlines of the quiet majority that steadies galaxies, binds clusters, strings the cosmos into a web, and, gently, holds us inside its architecture. Indirect hints in the sky: gamma rays, cosmic rays, neutrinos, searching for annihilation or decay. You step out of the underground halls and look up again. If dark matter rarely speaks to matter on Earth, it might still speak to the sky. In dense places, two dark particles might meet and vanish into familiar stuff: light, electrons, quarks, that cascade into radiation we can see. That's annihilation. Or, on very long timescales, a single dark particle might quietly fall apart into lighter things. That's decay. Either way, the universe becomes a vast detector. You just need to read its messages without being fooled by ordinary astrophysics. Start with messengers that travel straight. Gamma rays. They are high-energy light. Magnetic fields don't bend them, so they point back to their birthplace. If dark matter lights up this way, the best places to look are where the dark is densest or most abundant along the line of sight. Annihilation favors crowded hearts, the inner galaxy, dwarf centers, cluster knots, because encounters are common. Decay favors total inventory, wherever a long column of dark matter lies between you and the far side of the sky. The galactic center is the loudest stage. If our halo is deep and steep, its core could glow in gamma rays from rare meetings. Telescopes see a busy scene: pulsars, shock fronts, gas lit by cosmic rays, and vast lobes above and below the center. In that crowd, some patterns have looked a bit too round and smooth, as if a diffuse component hid in plain sight. But many faint pulsars can mimic that glow. The city's heart is bright, but confusing. So observers learn to love the quiet suburbs, tiny satellite galaxies that orbit ours like a whisper. These dwarf spheroidals are close enough to weigh and dim enough to keep their own light low. Point a gamma-ray telescope at a dwarf and see nothing, and that nothing is powerful. Stacking many such nothings sets strong limits on how often dark particles can annihilate. If a few dwarfs someday whisper the same subtle excess with the same energy shape, that chorus will be hard to ignore. Clusters offer a different promise. A cluster is a deep bowl of dark matter. Its inventory is enormous. For decay, that matters most. A gentle, widespread glow with the right spectrum, seen from several clusters at the right brightness versus distance, would be a crisp hint. For annihilation, clusters are noisy. Their hot gas and energetic particles complicate the view, but lensing maps help separate mass from glow. The spectrum matters too. Annihilation often makes a broad bump of gamma rays, but sometimes an almost monochrome line, a narrow spike at one energy. Nature rarely makes such lines at high energy. A true, sharp line that points to dark, rich targets and repeats across them would be a stop-and-look-again moment. Even without a line, a cutoff at a particular energy, a hard edge, can hint at the parent mass. Now, change messengers. Cosmic rays, electrons, protons, and their antiparticles carry energy but lose their birthplaces to tangled magnetic fields. By the time they reach us, maps blur, composition speaks. If annihilation or decay favors leptons, you might see an excess of positrons rising with energy. If it favors quarks, you might see a small bump in antiprotons. If fortune smiles, antinuclei, like antideuterons, appear. Backgrounds there are tiny, so a few would be a huge clue. Cosmic ray work is patience and subtraction. Nearby pulsars can also flood us with high-energy positrons. Supernova shocks can sculpt proton and antiproton spectra. The sun modulates low energies. Teams build careful background models, then ask what, if anything, is left. When a surprise rises, test whether it rhymes with other messengers. Does the same energy scale show in gamma rays from clean targets, or in neutrinos from places where gamma rays would be absorbed? Which brings you to neutrinos, the messenger that slips through almost anything. If dark matter piles up somewhere dense and annihilates or decays into channels that produce neutrinos, those ghosts fly out in straight lines. The galactic center is a natural target, again with caveats about backgrounds. But there is a special trick with the Sun and the Earth. If dark particles lose energy by scattering off nuclei, they can become trapped over long times, sink to the center, and annihilate. Gamma rays can't escape. Neutrinos can. A faint beam of high-energy neutrinos from the exact direction of the Sun, with the right energy habit and no day-night games, would be a clean signature. From Earth's core, the beam would point from beneath your feet. How do you tell a real dark matter signal from the universe's mimicry? Lean on 4 guides. First, the map. Annihilation brightens dense centers. Decay tracks total inventory. Dwarfs are dim but honest. The center is bright but complicated. A genuine signal places its light where the mass map says the dark lives and scales predictably across targets. Second, the spectrum. Seek shapes hard for ordinary sources to fake. A narrow gamma line. A clean cutoff. A spectrum repeating across dark, rich targets at the same energy. For cosmic rays, test whether rises can be explained by known sources. Save dark matter for what survives honest modeling. Third, timing. Dark matter should be steady on human timescales. Many astrophysical engines flicker. A heartbeat likely isn't the quiet majority. Fourth, the choir. A strong case sings in multiple messengers. A gamma excess from stacked dwarfs at a certain energy should line up with charged particle and neutrino constraints, all telling one story about mass and final states. Each messenger has favorite grounds. For gamma rays, a space-based surveyor maps the whole sky. Air Cherenkov arrays catch the most energetic photons with exquisite precision. For cosmic rays, spectrometers in orbit measure composition. Calorimeters weigh the fiercest arrivals. Balloons cross-check. For neutrinos, ice and water telescopes turn gigatons of clarity into ears. Blue streaks mark directions and energies. A cluster of events pointing to the Sun, too energetic for solar processes, would be a potent hint. A diffuse glow from the galactic center seen north and south would be another. Name the pitfalls plainly. The galactic center is a maze. Unresolved millisecond pulsars can mimic diffuse light. The positron excess is intriguing, but nearby pulsars are honest competitors. Use anisotropy and gamma halos to untangle. The antiproton story depends on how cosmic rays propagate. Do not mistake travel uncertainties for new physics. The Sun is complicated. Match any solar direction hint to the most conservative activity model you can build. There are clever strategies. Stack dwarfs to boost sensitivity. Mask bright sources and use ring maps to isolate faint extended glow. Use the Galaxies mass map to predict where signals should rise or fall. Chase antinuclei. Rare, but clean. What would success look like? A faint, steady gamma feature in several dwarfs. The same energy shape in each. Brightness scaling with their dark content. A modest echo in antiprotons that transport models can't erase. Neutrinos quiet where they should be, and perhaps gently present where they should. Fit together. One mass range and one family of final products explain the choir without straining any instrument's biases. That is how a whisper becomes a sentence. Until then, the work is restraint. Backgrounds honest, instruments steady, interpretations conservative. The reward is trust. When a real signal comes, you want the world ready to believe it, because every mirage was named and set aside with care. Carry 3 images. First, a city from a hill at night. Streetlights, neon, headlights, so many reasons for glow. Somewhere is a soft, round light that doesn't flicker. You learn its shape, then seek it in a quieter town and another. That is the dwarf search. Second, a message in 3 alphabets. The same sentence written in light, in charged particles, and in neutrinos should read the same way. If one letter differs, check your grammar. If all 3 match, read it aloud. Third, a coastline in fog. Gamma rays trace the cliffs. Cosmic rays swell and curl. Neutrinos walk straight through the mist. Mapmakers who combine all three draw the truest shore. So when you hear indirect hints in the sky, keep it clear and human. We scan the heavens for faint, steady signatures that match where the dark should be, sound like what it should make, and repeat across targets and messengers. We do this not to force a pattern onto noise, but to let a real pattern, if it exists, float up on its own. The universe owes us nothing, but it is generous with clues, and if dark matter leaves even a thin trail, the sky will keep whispering until we learn how to listen. Modified gravity? You arrive at a crossroads with a stubborn question. If galaxies rotate too fast for their visible matter, must we add invisible mass? Or could gravity's rules shift in the weakest fields? The first path is dark matter, the quiet scaffold you've been walking. The second is a change of script. Tweak the law, not the cast. That path is MOND, modified Newtonian dynamics, and a circle of relatives trying to grow the idea into a full story of the sky. Why is this tempting? Long before precision maps and deep lensing surveys, MOND put a finger on an empirical rhythm in galaxy data. Once accelerations inside a galaxy drop below a tiny threshold, rotation curves flatten in ways that track the visible matter. Hand MOND the starlight and gas of a spiral, and it often sketches the speed profile with uncanny accuracy using a single softness scale. It also recovers tight scaling laws, like the relation between visible mass and characteristic speed, that, in a pure dark matter picture, emerge only after the messy weather of star formation and feedback. Stand in front of a low surface brightness galaxy, a dim disk where ordinary gravity would predict gentle motion, and MOND smiles. My tweak kicks in early here, it says, and gets the speeds right more often than chance. At street level, in the outskirts of spirals, and in fragile dwarfs where accelerations are small, MOND looks like a tailor who knows your measurements before you speak. That predictive crispness is the heart of MOND's appeal. It isn't just curve fitting. In many cases, it wrote the answer in advance. If you lived only among disk galaxies, reading the slow sweep of their outer stars, you could ask whether gravity has a second mode in the low acceleration regime. But the universe is not only disks, it is clusters. It is the geometry of light. It is the baby picture in microwaves. To be a full script, a gravity rewrite must perform on every stage. That is where the struggles begin. First, galaxy clusters. MOND's tweak helps with some of the missing gravity there, but not enough. Even after the modification, the motions of cluster galaxies and the pressure of their hot gas ask for more pull than visible matter can provide. In the standard path, you shrug and say, that's the dark halo. In the modified path, you add something back, unseen ordinary matter or new particles, to balance the books. The clean alternative blurs. Second, gravitational lensing. Bending light is fully relativistic. Adjusting star motions isn't enough. Relativistic cousins of MOND add new fields so photons feel the modified pull. They can match overall lensing near some galaxies, but in colliding clusters where mass and light peel apart, or in tangled, strong lensing scenes, keeping lensing maps aligned with dynamics proves difficult. The mass map drawn by light bending still tends to sit with the galaxies, not the glowing gas, echoing the need for a substantial, non-luminous component. Third, the cosmic microwave background, the baby picture. Its pattern of hot and cold spots records how matter and gravity choreographed a glowing fluid. In the standard script, a large share of non-glowing, non-collisional matter deepens wells without joining the slosh, essential for the peak pattern. In MOND-like schemes without a comparable reservoir, the peaks strain. Relativistic extensions try to add fields that act like a dark component at early times. But each fix adds knobs, and the tidy no dark matter needed slips. Fourth, the growth of structure. From faint early wrinkles to today's filaments and clusters, there is a timetable. In the standard story, the unlit component falls in early, seeding wells that luminous matter later fills. Modified gravity worlds without a true dark sector struggle to plant deep seeds fast enough while still honoring the microwave constraints. Some models add ingredients so the modification behaves, on large scales and at early times, as if there were a dark backbone. Hold this with a metaphor. Imagine a class. One student, Mond, answers homework on disk galaxies with impressive confidence and minimal fuss. On the exam, light-bending clusters the early universe. The same student struggles unless allowed extra notes and helpers. Meanwhile, the dark matter student sometimes explains why small-scale predictions aren't razor-sharp. Feedback is rowdy, but passes the comprehensive lensing, baby picture, structure growth, clusters, the lot. The conversation has matured. Modified gravity proponents built relativistic frameworks that bend light and pointed to crisp tests, like the relation between visible mass and acceleration. They note that a standard dark matter galaxy still must explain why messy baryonic histories land so neatly on Mond-like relations. Dark matter modelers, in turn, showed that baryons are not bystanders. Winds from stars and black holes can reshape central densities, alter rotation curves, and tighten scaling laws, helping the standard picture reproduce relations Mond highlighted. What began as a duel is now a dialogue. One side announcing clean patterns, the other showing those patterns can arise from realistic galaxy weather riding on an unlit scaffold. Where should you place Mond and kin? Credit where due. They predicted features of galaxy rotation early. They named a small acceleration scale, marking a behavioral threshold. They kept cosmology attentive to simple, empirical laws, limits to keep. Clusters still ask for extra mass beyond baryons under Mond-like rules. Lensing, especially in mergers, tends to track galaxies, not plasma, implying a component that flows without drag. The microwave peaks and structure timing favor a genuine, non-slushing mass reservoir. Many relativistic cousins of Mond reintroduce fields that act like a dark sector on some scales. There's a philosophical edge. Changing gravity feels economical. Fix one rule, explain many puzzles. But economy also means fewer ad hoc exceptions when the stage widens. If your rewrite needs added particles for clusters and again for the early universe, economy fades. Conversely, the dark matter path begins with an unseen actor, which sounds like an addition, but that actor plays consistently on every stage, bending light, shaping the baby picture's rhythm, growing the web, while baryons provide the local drama, carry three images, the quiet street and the interstate. On the quiet street, the outskirts of a spiral, Mond knows the traffic from the houses alone. On the interstate, the large-scale sky, the standard mix with a lot of invisible freight keeps the schedule. The tailor and the architect. Mond is a gifted tailor of galaxy clothes, but the city still needs an architect for bridges and load-bearing walls. Lensing, the baby picture, and the web are the bridges, the echo and the choir. Galaxy rotations are a clear echo. Mond catches it well, but the universe sings in a choir. Photons bending, clusters colliding, early waves freezing into peaks. When all voices join, the harmony points to a quiet section you cannot see, but can hear through the music it shapes. So when you hear modified gravity, Mond and friends, keep it balanced and human. A clever rule captures the dance of stars in many galaxies with disarming simplicity. It is a real clue, but the full sky asks for more than a local step change. It asks for a framework that bends light correctly, honors the early universe drumbeat, grows a web on time, and explains why mass and glow part ways in a collision. Today, the path that satisfies all of that most cleanly still includes a large, quiet component that doesn't shine. You can appreciate the tailor's craft and still trust the architect's plan. The modified rule taught us where to look and what to measure. The invisible scaffold ties the story together. Between them is a productive tension that keeps observers honest, modelers busy, and the night sky richer than any single idea could make it alone. Small-scale puzzles. Cusp core, too big to fail. Missing satellites, status, and fixes. Walk down from the grand cosmic web into the local neighborhoods. Faint dwarfs, satellite swarms, the inner hearts of halos. Here, 3 puzzles have kept astronomers honest and creative. Each is simple to say, tricky to solve, and deeply useful, because fixes that work at street level must also leave the highway intact. First, the cusp core question. Purely cold, collisionless simulations like to grow steep inner rises, cusps, where density climbs sharply toward the center. Many dwarfs, however, seem to have cores, flatter, softer hearts. You feel the difference in how gas rotates and how stars drift inside a kiloparsec. What could blunt the point? One answer is the weather of ordinary matter. In small galaxies, star formation is bursty. Gas piles in, ignites, then supernova winds push it out. That push-pull shakes the central potential like a slow bell. With enough cycles, dark matter orbits expand a little. A cusp relaxes into a core. The effect is strongest where gravity is weakest, just the place dwarfs live. Another answer sits in the dark sector. A warm flavor trims the tiniest seeds before they grow, favoring gentler centers. A self-interacting flavor lets dark particles nudge one another over time, transferring heat inward and rounding the spike. Even a small nudge, repeated for billions of years, can soften a center without touching the outer halo. Measurements matter too. Tilt a galaxy and non-circular motions masquerade as flatness. Stir gas with feedback, and the rotation curve gains wiggles that hide the true slope. Stars and gas may trace different depths of the same well. When you combine careful 3D kinematics with realistic feedback, some classic cores look less dramatic. Others hold up. The honest summary. Many dwarfs truly prefer soft centers. Some tolerate steeper ones. And the mix can be explained by star-driven shaking. Plus, perhaps, a hint of dark sector softness. Street-level diversity without breaking the highway. Second, the too big to fail problem. Early Milky Way-like simulations produced several subhalos so dense that, if they hosted stars, the brightest satellites should have shown much higher internal speeds than we observe. These halos looked too big to have failed at forming bright dwarfs. Where did the density go? Part of the answer sits in the host's disk. A real Milky Way has a heavy rotating sheet of stars and gas. Satellites passing near it are tugged, shocked, and stripped, losing central mass and sinking. Part sits in the dwarf's own histories. Bursty feedback can deflate their cores. Reionization in the early universe quenched star formation in many halos before it began. Part sits in the census. As surveys go deeper, more ultrafaints appear, raising the observed count. And part sits in bookkeeping. Our galaxy's total mass and the orbits of key satellites carried wide error bars. Revise those, and the sharp edge softens. Today, too big to fail is smaller. Not gone everywhere, but much reduced when disks, tides, feedback, and updated satellite counts are included. Remaining tensions are now specific targets, not blanket verdicts. Third, the missing satellites problem. Simulations predict a steep rise in the number of small subhalos. The sky, at first, showed far fewer faint companions than expected. 2 neat fixes sit side by side. First, we weren't seeing them. Many satellites are tiny, dim, and low surface brightness. Early surveys missed them outside their footprints. As coverage deepened and widened, dozens of ultrafaints emerged, and models that include realistic completeness now bring predicted and observed counts into closer rhyme. Second, most tiny halos are dark. Reionization and feedback keep the smallest from ever forming many stars. The halos are there. The lanterns are off. New techniques check the dark directly. Strong lensing arcs carry tiny wiggles from unseen subhalos along the line of sight. Stellar streams around the Milky Way record scars where invisible clumps pass through. Both approaches find hints of the right amount of small-scale structure, with room still to tighten. Add in 21 centimeter mapping of faint gas and deeper time-domain surveys that can catch brief flares from otherwise hidden systems, and the outlook sharpens further. The direction of travel is encouraging. The more we look, the less is missing. A useful split across all three puzzles is field dwarfs versus satellites. Satellites live under a host's tides and ram pressure, so disks and hot halos reshape them. Field dwarfs evolve more quietly, making them cleaner tests of feedback and the dark sector. If cores appear widely in field dwarfs with calm histories, feedback alone must be efficient. Or a small dark sector softness is helping. If cores show mainly where tides and bursts are fiercest, environment is the chief sculptor. You can also separate fixes by signatures. Feedback-driven cores often correlate with bursty star formation histories, puffed stellar distributions, and outflow-shaped gas. Dark sector softness tends to leave rounder inner halos, even when recent star formation is quiet, and it may lower central densities of satellites that never had much gas. Stream gaps and strong lensing wiggles weigh the invisible population directly. If those counts stay high while satellite galaxies remain modest, warm or self-interacting tweaks must be small, with feedback doing most of the carving. A few case notes help anchor the picture. Fornax shows extended star formation and multiple globular clusters. Tides and feedback together likely eased its core. Draco is old and gas-poor, with little sign of recent bursts. If it prefers a core environment or a small dark sector nudge, may be at work. Ultra-diffuse galaxies and clusters, some surprisingly rich in globulars, hint that tides and early quenching can build large, faint systems without breaking the dark scaffold. 2 extra threads round out the small-scale story. Diversity of rotation curves. Galaxies with similar total mass can show very different inner rises. Feedback naturally spreads those shapes by stirring gas differently from system to system. Mild dark sector softness widens the spread a bit more. The key test is whether simulations that include realistic star formation histories reproduce not just the average curve, but the scatter, and they increasingly do. Planes of satellites. Around the Milky Way and Andromeda, subsets of satellites seem to line up and co-rotate in thin sheets. Are these long-lived structures or snapshots of groups caught mid-infall? Simulations with rich accretion histories and full disk physics produce temporary alignments often enough to take the edge off the surprise, but the sharpest, thinnest planes remain lively tests for how hosts grow and how tides prune. If you want a quick status card, cusp core. Soft centers in many dwarfs look real. Bursty feedback explains a lot. Small doses of warm or self-interaction can help. Better 3D kinematics, multiple tracers, and gas modeling are the keys. Too big to fail. Largely softened by a live galactic disk, tidal stripping, feedback, revised host mass, and added satellites. Residual tensions linger in a few systems, and in some field dwarfs, good tests ahead. Missing satellites. Counts rise with deeper surveys and completeness corrections. Reionization makes many halos dark. Lensing substructure and stream gaps support a healthy crop of small clumps. What to watch next? Proper motions from precision astrometry to nail orbits and tides. Wide, deep imaging to finish the satellite census and map diffuse light around dwarfs. Gas-rich dwarf kinematics to separate true cores from measurement tricks. Strong lensing samples large enough to weigh substructure statistically. Stream cartography that multiplies clean gap detections. Simulations with lively baryons and subtle dark sector variants that produce mock skies processed like real data. A shared playbook, observers and simulators using the same cuts and systematics, is the fastest path to closure. There is a thematic both-and running through the fixes. Both dark sector simplicity and messy baryonic weather. Both early pruning of seeds and late-time reshaping of centers. Both better data and better models. The large-scale triumphs of the cold scaffold remain. The small-scale details teach us how stars, gas, tides, and perhaps a hint of softness in the dark share the same stage. Carry 3 images as you leave this block. The snowpack. Fresh snow forms a sharp drift. Sun and wind round it. Dwarfs begin pointed. Feedback and time soften the crest. The tight shoe. a sub-halo that seemed too snug for any dwarf relaxes as the leather warms. Tides, feedback, and reionization ease the fit. The city map. At first, only main roads. With better streetlights, alleys appear. Some neighborhoods stay dark by design, but the map fills in. So when you hear small-scale puzzles, keep it human and balanced. 3 tidy questions that forced us to measure more carefully, model more honestly, and accept that the universe can keep its grand blueprint while still fussing over the trim. The result is a sturdier story, one where the scaffolding holds, the local carpentry matters, and the smallest rooms finally feel lived in. The bullet cluster. Gas goes one way, gravity another. Matter we can't see separates from plasma. Imagine 2 galaxy clusters rushing toward each other across deep space. 2 crowded cities of galaxies, each wrapped in a broad, quiet halo. When they meet, it isn't a smash and halt, it's a pass-through. The stars are so spread out that most slip by without touching, but between those stars lies hot, thin plasma, gas heated to extremes, shining in high-energy light. That gas behaves differently. It collides, it drags, it slows. Right after the encounter, the scene is layered. The galaxies from each cluster have already moved ahead, gliding on with little fuss. The wider, deeper halos that surround them, made mostly of matter we can't see, also glide ahead. Meanwhile, the plasma has piled up between the 2 swarms, shocked and bright, like a wake left by something that has already passed. In one direction you see a sharp, bullet-shaped front in the gas, the signature of compression. A step farther along you find the swarms of galaxies, and if you weigh the whole system by how it bends background light, using gravity as your measuring tape, the peaks of mass line up with the galaxies, not with the glowing pile of gas. That last point is the headline. In clusters, plasma is the bulk of the visible matter. If visible matter were the full story, the center of gravity would sit where the gas stopped and gathered. It does not. The strongest pull travels with the galaxies, not the jammed plasma. Gravity follows the travelers. Hold 3 layers in your head. Layer 1. The ordinary view, a field of galaxies from 2 clusters passing through each other, like 2 flocks crossing paths. Layer 2, the high-energy view, a bright cloud of shocked, super-hot gas lingering between them, with a crisp, bullet-like edge where the gas slammed into a headwind and heated up. Layer 3, the gravity view, a map drawn from the way background light is bent as it passes through. Those mass peaks sit with the galaxy swarms on either side, not with the central gas. The weight and the glow are offset. That offset is the signature. It says, in plain language, most of the matter doesn't collide like gas. It doesn't stick. It slips through and keeps going. Call it dark matter or the quiet majority. Either way, it behaves differently from plasma right in front of us. Add a little texture. As the smaller cluster punched through the larger one, its gas felt a strong wind. That wind created a shock front, a sharp edge where the gas was compressed and heated, shaping the bullet. The stars did not feel that wind. Neither did the deeper, unlit halo around them. So the stars and the halo moved on, while the gas lagged behind. In a single snapshot, the system sorts itself. Leaders made of galaxies and invisible mass, and a glowing trailer of plasma. This picture is more than striking. It is a clean test. If the only mass were the bright stuff, the mass peaks and the bright gas would sit together. They don't. If the unseen mass interacted strongly the way gas does, it would have piled up as well. It didn't. Instead, the main weight shows up, where the collision left the least mark, Out with the galaxies that sailed through. Scientists ask careful questions of any bold claim, so they check the angles. Could the gravity map be fooled by matter stacked along our line of sight? Teams model the geometry, compare with similar systems, and find the same pattern. Gravity tracks the galaxies, not the stuck plasma. Could hidden ordinary matter explain the offset? If it were ordinary, it would behave like gas, feeling the headwind and stopping. It doesn't. The simplest, most consistent reading remains. Most of the mass is unlit, rarely collides, and kept moving when the bright gas did not. Keep two simple analogies close for narration. First, two cars pass through a cloud of confetti. The metal frames keep going. The confetti slams together and hangs in the air between them. Later, if you weigh the scene by how it tugs on, passing leaves, most of the pull sits near the cars, not the confetti cloud. In the bullet cluster, the cars are galaxies, plus their invisible halos. The confetti is the hot gas. The leaves are the background light, bent as it goes by. Second, a river splits around a rock. Froth piles up at the rock. The fish swim on. If you measured the momentum of the river, you'd follow the fish, not the froth. The froth is bright. The fish carry the flow. Now widen the frame. The bullet cluster turns gravity into a courtroom exhibit. Exhibit A, the galaxies. Quiet beacons moving ahead. Exhibit B, the glowing gas, stopped and shocked in the middle. Exhibit C, the gravity peaks, mapped by bent background light, aligned with the galaxies, not the gas. Together they say, the main mass is not where the glow is. You can point to the offset and read the sentence without jargon. This scene also teaches character. Whatever most of the mass is, it glides through itself and through ordinary matter with very little friction. It shapes the large-scale architecture, but doesn't smear out in a crash. That behavior sets limits on how often the unseen bumps into itself. In plain terms, dark matter seems to be a quiet traveler, not a sticky fluid. It helps to remember that the bullet cluster is not alone. Other merging clusters echo this lesson with their own geometries and timings. Each shows some version of the same separation, gas that collides and lingers, and deeper mass that moves on. One case is compelling. Many cases make a chorus. What does this add to your bigger story about the invisible majority? First, it complements the steady clues. Flat speeds in galaxy outskirts tell us the bright disks are held by wider halos. Rings and arcs from strong lensing map, dense clumps beyond what light can explain. Weak lensing sketches a vast web where mass spreads wider than glow. The bullet cluster adds a timed event, a cosmic fender bender, showing in motion that the dominant mass does not act like gas. Second, it strengthens the way we use lensing as a ruler. Strong lensing around cluster cores marks where gravity pulls most deeply. Weak lensing across the outskirts fills in the wider envelope. In the bullet cluster, both point to the same places. The leaders, not the traffic jam. Third, it grounds the conversation about alternatives. Could a change in our understanding of gravity alone explain the offset? Changing gravity might help with motions, but here we have separation. The bright plasma sits in one place. The gravity peaks sit elsewhere with the galaxies. That visual misalignment is difficult to mimic by adjusting gravity alone without also adding unseen mass. The simplest story still fits best. There is a large component that doesn't shine and doesn't collide like gas. For your script pacing, a clear talk-through sequence works well. Set the scene. Two clusters approach and pass through. Show the layers. Galaxies ahead. Shocked gas in the middle. Gravity peaks with the galaxies. Read the meaning. Most mass is not the glowing gas. It is the quiet halos that pass through. Close the loop. This behavior matches what we see in flat galaxy speeds, in lensing rings and arcs, and in weak lensing maps of the web. End with a simple human-sized thought. In a crash, the loudest part isn't always the heaviest. The brightest cloud is not the center of gravity. The universe is telling you, as clearly as it can in one picture, that the scaffold holding galaxies together is quieter than the glow, harder to stop than the gas, and faithful to its path even when everything bright gets stuck. That is why the bullet cluster matters. It's a single, vivid frame where glow and gravity disagree about where the center should be, and gravity wins. The missing mass, Zwicky galaxy, clusters way more than their light implies in 2, 3, 4 out, 2, 3, 4, 5, 6. Let your breath settle. Picture a great hall hung with distant lanterns, hundreds, even thousands, each lantern a galaxy with its own stars and stories. Gathered together, they form a galaxy cluster, a city of light inside a dark expanse, held as one by a shared pull. Almost a century ago, an astronomer named Fritz Zwicky stood at the edge of this city and asked a question that sounded simple but felt daring. Does the glow tell the whole truth about the weight? He watched how the cluster's galaxies moved, each one sliding past its neighbors like small islands, drifting in a calm sea. He listened to the starlight for hints of motion and compared those motions to the brightness he could count. If light were a faithful scale, the cluster should have been looser, more fragile, with many galaxies peeling away into space. But the city held. The streets were busier and brisker than the streetlights could justify. Zwicky named the difference missing mass, a quiet share not seen in the glow, in 2, 3, 4 out, 2, 3, 4, 5, 6. It was a brave claim. The tools then were young, the data rough. Zwicky himself could be sharp-edged, and sometimes a sharp-edged messenger makes people doubt the message. But the sky is patient with us. Across the decades, better instruments returned to those same cities of galaxies and asked the same question. The answer kept repeating. The motion is too lively for the visible alone. The cluster is deeper than it looks. Think of a bowl. The galaxies are marbles rolling inside. If the bowl were shallow, the quick marbles would leap the rim and scatter. They don't. They stay in the bowl. That means the bowl is deeper, shaped by more than we can see with ordinary light. At first, astronomers looked for missing pieces in the familiar, perhaps clouds of gas, too dim to notice. Later, X-ray eyes in space revealed that clusters hold vast oceans of hot, thin gas, ordinary matter we had not seen in visible light. Yes, that added weight, deepening the bowl. But even after counting galaxies and gas, the bowl was still deeper than the glow could explain. The difference remained in 2, 3, 4 out, 2, 3, 4, 5, 6, 6. Then came a way to feel the depth without relying on light at all. When a massive cluster sits between us and more distant galaxies, it gently warps their paths of light, like thick glass bending a scene behind it. Sometimes the effect is a soft stretch. Sometimes it paints long arcs across the sky. By mapping those distortions, astronomers can draw a picture of where the mass is, even if that mass is dark. Again and again, the picture that emerges is heavier and broader than the visible parts suggest. The mass map and the light map do not match. The mass map is larger, quieter, decisive. Out. 2, 3, 4, 5, 6. Return to Zwicky for a moment, a person alone with a telescope and a stubborn idea. He wasn't dressing the sky in clever words. He was trusting behavior over brightness. The galaxies were moving with a confidence the glow could not support. He said so. And though the world took time to catch up, the pattern holds. Clusters carry a hidden share, a hush beneath the chorus of lights. You've already met a related clue in spiral galaxies, where outer stars circle too steadily for the visible matter alone. Clusters tell the same story at a grander scale, not just stars moving too fast, but entire galaxies doing it. Whole lanterns gliding in a hall whose floor is lower than it looks. Different scene, same theme in 2, 3, 4 out. 2, 3, 4, 5, 6 lay the clues on the table like cards. Lively traffic. The swarm of galaxies moves with energy. If you trust only their combined glow, many should not be held. But they are, together, enduring, hidden oceans. X-ray views reveal vast, hot gas filling the spaces between galaxies. It is real weight, ordinary matter we've failed to see in visible light. Yet still not enough to explain the grip by itself. Warped views. Background galaxies appear stretched and shifted as their light passes the cluster. This bending draws a map of mass that outgrows the light. Taken together, the cards make a firm picture. The city weighs more than the streetlights suggest. The bowl is deeper. Most of the holding is done by something that doesn't shine. Out. 2, 3, 4, 5, 6. Breathe gently and widen the lens. In some clusters that have collided, 2 cities passing through each other, the hot gas slams together and lingers in the center, slowed by its own interactions. But the main gravitation, the quiet heft traced by bent light, moves ahead with the galaxies, almost as if that mass barely notices the crash. The light map and the mass map separate for a time, like travelers on different lanes of a road. It's a clean visual hint that the dominant matter is not the glowing gas we see. It's a quieter traveler gliding through. In 2, 3, 4 out. 2, 3, 4, 5. This is how the story matures. First an idea with rough edges, then a chorus of evidence from many angles. Careful teams measure motions. Others weigh clusters by how they bend distant light. Others still take the temperature of the hidden gas and add its weight to the count. Across instruments and eras, the answer keeps harmonizing. Yes, you can question each method on its own, but together, like different singers finding the same note, they reveal the tune. There's a human lesson tucked inside this. When you judge a place, don't rely on the brightness of its signs. Notice the steadiness of its life, the way people return, the way the town holds together in the quiet hours. The clusters teach us the same. The glow gives you a map of lamps. The motions give you the map of the ground. 2, 3, 4, 5, 6, you might wonder. If so much is unseen, why trust it? Because the unseen keeps leaving fingerprints we can test. The pattern repeats across clusters of many kinds, tight and relaxed, nearby and far. The hidden share is not a delicate trick. It's a reliable habit of the universe. When different questions point to the same answer, the answer earns your attention. And what exactly is this missing mass made of? We speak honestly, we do not have the final name yet. There are good candidates, quiet, seldom interacting particles, or other, more delicate possibilities. And there are careful experiments listening for the faintest taps in underground halls and in the cold of space. So far, the sky keeps its quiet. That's okay. You don't need all the labels to trust the outline. First, learn the shape in 2, 3, 4 out. 2, 3, 4, 5, 6. Hold the image of a cluster again. Lanterns moving, yet the city remains a city. Feel the bowl under them. Wide, deep, invisible to your eyes, undeniable to their motion. Zwicky heard the disharmony between light and behavior and gave it words. Later generations tuned the instruments, played the song again, and found the same melody. Clearer, stronger, unmistakable. Zoom in, just for a heartbeat, to our own place in this story. The Milky Way belongs to a small neighborhood of galaxies, and beyond that neighborhood lies a larger assembly, a loose community drawn into greater gatherings still. Each gathering is shaped by the same quiet architecture. We live not just under stars, but inside a structure that light alone can't draw. The night sky, you know, is a bright face laid over a deeper frame. Out. 2, 3, 4, 5, 6, and here is the soft philosophy. Often in life, what truly holds you is not the loud thing in the center, but the quiet groundwork, the sleep you got, the habits you stacked, the friends who show up without a trumpet. clusters echo that wisdom. Judge not only by the glow, but by the staying power. The missing mass is simply the universe's way of saying, there is more here than what shines. In 2, 3, 4 out, 2, 3, 4, 5, 6. As you exhale, let the hall of lanterns dim in your mind, leaving the feeling of the bowl, the assurance beneath motion. Zwicky named the absence. Modern eyes trace the presence. Together they handed us a way to weigh truth when brightness is not enough. Trust the behavior, map the depth, honor the quiet share. Good. Let's keep going. Too fast galaxies flat rotation. Outer stars orbit too quickly for visible mass alone in 2, 3, 4 out, 2, 3, 4, 5, 6. Let your breath settle. Imagine a spiral galaxy hanging in the dark like a slow pinwheel. Bright center, soft arms laid out like ribbons of frost. If you close your eyes, you can almost feel it turning. Nearer the hub, stars circle quickly. Out along the edges, you expect a quieter drift. That's how most spinning things behave in the world we know. The outer rim of a windmill moves fast, but only because the whole blade is rigid. For loose swarms, like birds around a tree, the farther ones should ease their pace. Now open your eyes to what the sky actually says. Astronomers measure how fast the stars and gas are moving as they go around their galaxy. They do this by reading tiny changes in starlight. Subtle tugs toward red or blue that whisper, coming or going. Line up those whispers across a galaxy, and you get a simple story about speed. In 2, 3, 4 out, 2, 3, 4, 5, 6. Here's the surprise. Far from the center, where the glow thins and the star fields are sparse, the speeds don't sink the way our everyday sense would predict. They level out. They stay high. Picture a city where the downtown is bright and heavy with buildings, and the suburbs are soft and dim. You'd expect traffic to slow as the roads thin out. Instead, you drive to the edge of town and find every car still cruising like it's rush hour. Galaxies do that. Their outskirts keep moving fast, as if something invisible is setting the cruise control. How do we know it isn't just a trick of light? Because the pattern repeats. In galaxy after galaxy, big and small, elegant spirals and messy dwarfs, the outer regions keep their pace. Even clouds of gas, not just stars, show the same stubborn speed. Different telescopes, different teams, different decades, the same flat shape to the speed story. Not a slump, not a fade, steady in 2, 3, 4 out, 2, 3, 4, 5, 6. Think of it this way. If only the shining parts counted, a galaxy would be like a lantern with most of its weight in the flame and very little in the glass. The farther from the flame you go, the weaker the grip should feel. But those outer stars are feeling a strong, consistent hold. Something is there to keep their paths tight and sure, even where the light is thin. We don't see the hand. We see the steadiness of the dance. You can picture the hidden something as a great, dim halo, much larger than the bright disk, stretching far beyond the last visible stars. The glowing spiral is just the lantern's flame. The halo is the glass sphere around it, wide and quiet. Inside that sphere, everything turns with confidence, even at the edge. Out, 2, 3, 4, 5, 6. There's a tender kind of logic here. In your own life, you've learned to trust evidence that arrives sideways. You don't always know a person by what they say, but by what they show, by the way a room feels when they enter, by the care they put into small things. Galaxies are like that. Their edges tell the truth about what holds them. The truth is simple. The visible isn't enough. Let's walk through the clues without rushing. First, the bright center. It explains why the inner parts spin lively. No surprise there. Where there's more stuff, there's a stronger hold. Second, the middle zones. They keep pace instead of easing off. Interesting. Third, the outskirts, still cruising, far past the glow. That's the headline. The outskirts should have slowed long ago, unless they're traveling through a wider, heavier embrace than our eyes can see. In 2, 3, 4 out, 2, 3, 4, 5, 6. Could the stars be lighter than we think? Heavier? Could hidden gas be doing the job? These questions were asked again and again. More gas helps a bit, but not enough. And the kinds of gas that could hide well don't add up to the steady speeds we measure. Dust glows in other ways when warmed. It can't stay secret at scale. What's left is the quiet possibility that most of the mass is something else. Something that doesn't shine, doesn't block, doesn't smear our view with haze. Something that simply holds. This is why the Too Fast Galaxy story matters. It isn't a single shocking snapshot. It's a chorus that rises from thousands of careful readings. Every flat, steady speed at the edge is a note in that chorus. Together they sing. There's a wide, invisible structure here, and the bright disk is only the surface of it. Out. 2, 3, 4, 5, 6. Let your mind step into 2 images. Image 1. The merry-go-round. Children ride painted horses. The platform spins as one. Everything is bolted together, so speed at the edge is forced to match speed near the center. A galaxy is not like this. Stars are not bolted down. They're more like birds in a shared sky. If only the shining mass counted, the outer birds would drift slower. But they don't. Something is doing the bolting quietly. An unseen frame. Image 2. The campfire and the night. The flames and logs of the visible galaxy. Warmth fades as you walk away. Now imagine that as you step into the trees, you still feel a steady heat, like a gentle, even warmth filling the forest. Not as bright as the fire, not flickering, just there, broad, calm, holding the night at one temperature. That's the halo. Not hot, not glowing, but present in the way the world feels. In 2, 3, 4 out, 2, 3, 4, 5, 6. The beauty of this clue is how it links to others. The same invisible frame that keeps edge stars moving also helps bend the paths of distant light. When a galaxy or a cluster sits between us and something farther away, the same quiet bulk helps draw newborn galaxies together in the early universe, guiding where structures form along the vast cosmic web. Different paths, same destination. A large share of a galaxy's there-ness is unlit. And yet, even as we accept the outline, we honor the mystery. What is this dark material made of? We have good guesses and careful experiments listening for faint taps in quiet rooms under mountains, or for shy signs in space. For now, the sky answers with patience. Learn my shape first. Names will come. Out. 2, 3, 4, 5, 6. Bring it home to our Milky Way. Our sun orbits in a long, slow loop around the galaxy's heart, carried not only by the pull of bright stars and clouds, but also by that wide, dim embrace. Somewhere beyond the furthest star you can see on a crisp night, the halo continues, silent, steady, faithful to the edge. And there's a soft lesson tucked inside all this. Sometimes the best measure of what holds your life together isn't the obvious center, your tasks, your titles, your calendar, but the way the edges keep their pace. The calm you still feel when the day is thin, the steadiness that doesn't fade when the bright parts are over. Something unseen in you is doing the holding in 2, 3, 4 out, 2, 3, 4, 5, 6. So when you hear the phrase too fast galaxies, let it translate into something human and clear. The outskirts aren't coasting, they're confidently moving because a larger, quieter structure is carrying them. That's the heart of the clue. Simple, stubborn, luminous in its own unlit way. As you exhale, picture a spiral again, arms like rivers of frost. Feel the edge glide with the same surety as the middle. You don't have to see the frame to trust the turn. The universe is telling you, kindly and repeatedly, that the story of light is written on a page of shadow, and both are needed to read the book. Good. Let's keep going. Warm and self-interacting dark matter. You've met the standard picture. a cold scaffold that clumps early and holds galaxies in deep wells. It works on the largest scales, the cosmic web, cluster counts, the grand sweep of structure. But in the smallest neighborhoods, dwarf galaxies, halo centers, the exact number and character of satellites, you find details that invite a closer look. Some dwarfs seem to have softer centers than a simple, cold and collisionless story would prefer. Some halos look rounder than expected. Some subgroups of satellites are fewer or gentler than the sharpest versions predict. None of this breaks the big picture, but it invites small refinements. Two families step through the door with clear personalities: warm dark matter and self-interacting dark matter. Each keeps the large-scale successes intact while changing the texture of the small. Each offers testable signatures in galaxy cores, in satellites, and in halo shapes. Start with warm dark matter. Warm, not because it glows, but because its particles moved a bit faster in the young universe than their cold cousins. That early speed matters. Picture planting a field with fine seeds on a breezy day. A light wind blows away the tiniest seeds before they take root. Only patches above a certain size sprout. Warm dark matter does something similar. Its early motion smooths away the smallest clumps before gravity can tighten them. The result is a suppressed small-scale garden. Fewer ultra-tiny halos, fewer ultra-faint satellites, and a cosmic web that looks familiar in broad strokes, but is less finely stippled at the tiniest scales. This smoothing reshapes dwarf galaxies. With fewer tiny seeds, you expect fewer satellites around a Milky Way-like host. The satellites that do form tend to be less concentrated in their cores, easing long-standing tensions where simulated sub-halos seemed too tough compared with real dwarfs. Rotation curves lean toward flatter, gentler rises. And in the intergalactic medium, the thin gas that records the universe's faintest writing, warm dark matter leaves a cleaner script, fewer sharp small-scale wiggles in the absorption pattern from distant beacons. Warmth, however, has limits. The baby picture of the universe and the ripples in intergalactic gas both like a certain amount of fine grain. Smooth too much, and you erase structures we clearly see. So the warm option can't be too warm. The sweet spot is narrow. Just enough early motion to soften the tiniest clumps and reduce the swarm of satellites, but not so much that you wash out delicate threads across deep space. In practice, warmth likely trims the embroidery rather than redesigning the fabric. Shift to self-interacting dark matter. Here, particles are still dark and abundant, but they occasionally nudge each other when they pass. Not often, far less than air molecules, but often enough over a galaxy's lifetime to matter in the center. Imagine a crowded square at noon. If no one reacts, the densest core stays dense. If people yield and share a bit of space, gentle shoulder taps, small step-asides, pressure in the middle eases, and the crowd spreads. Self-interactions do this for halos. They move energy inward and outward, softening the sharp cusp predicted by the simplest cold picture into a soft core in dwarfs and many low-mass galaxies. This pressure sharing tends to round halos too. Collisions between dark particles randomize orbits, making inner shapes less needle-like and more spherical. In larger halos, groups and clusters, the same nudge produces broader, less peaked centers, which affects how strongly those halos bend background light and how hot gas sits in equilibrium. Self-interactions can be velocity sensitive, and that is a useful dial. In small systems where speeds are low, the nudge can be stronger, sculpting kiloparsec scale cores and rounder centers. In massive clusters where speeds are high, the nudge can be weaker, preserving the sharper mass distributions that lensing and X-ray maps prefer. This stronger for dwarfs, gentler for giants personality helps the model pass a key test: colliding clusters like the bullet cluster. There, the dark must flow through with little friction. Heavy self-drag would have stranded the mass with the glowing gas. A velocity-dependent nudge sidesteps that trap, quiet in the crash, active in the calm of small galaxies. Both families speak to three debated details: pre, cores versus cusps. Classic cold halos want steep inner rises. Many dwarfs look flatter. Warm smooths initial seeds, so the densest piles never sharpen fully. Self-interactions move energy around after formation, softening what would have been steep. Baryons, stars and supernova winds also stir centers, so the true picture likely blends stellar feedback with either cold's baseline or these dark sector tweaks. Warm alters the starting canvas. Self-interactions adjust the finished painting. Satellites and the too tough problem. Some cold-only simulations gave bigger subhalos denser centers than the brightest dwarfs seem to have. Too big to fail. Warm reduces early ultra-dense subhalos. Self-interactions deflate central densities over time. Either path brings simulations closer to data. Meanwhile, new ultra-faint dwarfs keep turning up, and better star formation modeling has trimmed the gap. Expect a both and, improved baryonics plus a small warm or self-interacting twist. Galaxy and halo shapes. Collisionless halos can stay triaxial, especially in centers. Self-interactions nudge them toward rounder forms. Warm, by pruning tinier seeds, indirectly favors smoother inner architecture, which can also lean round. Observers read shapes through lensing, stellar motions, and hot gas maps. The trend, often rounder centers than the sharpest cold predictions, sits comfortably with a bit of dark sector softness. Separate the signatures. Warm changes the initial power to build structures. Fewer tiny clumps form at all. Self-interacting keeps initial clumpiness but redistributes energy later. Cusps relax into cores. Shapes round out. That difference matters. If you search strong lensing arcs for tiny subhalo wiggles and still see plenty, warmth must be modest. If dwarf centers stay soft despite stellar fireworks, self-interactions may be lending a hand. There's a time story. Warm declares preferences early. The web grows with fewer twigs. Self-interactions work slowly, reshaping wood already grown. In clusters, strong self-drag would leave obvious offsets between galaxies and dark mass in many collisions. The sky shows mass mostly keeps up with the galaxies. That doesn't kill self-interactions. It just keeps the allowed nudge small in fast systems and perhaps stronger in slow ones. How do you listen for these variants? Map dwarf galaxies, star motions, gas rotation, central mass profiles. Softer centers that persist hint at a dark sector role. Count satellites around Milky Way mass hosts. Fewer ultra-tiny companions and gentler centers favor warm or self-interacting twists. Read the cosmic parchment. The absorption pattern from distant beacons reveals how much tiny structure the universe allowed. Too smooth means too warm. Too wiggly means cold or only slightly warm. Trace halo shapes in lensing and X-ray maps, checking how round centers are and how this varies with mass as a velocity-dependent nudge predicts. Watch strong lensing arcs for substructure wiggles. A healthy crop of small clumps pushes back on bold warmth. A lack of very dense clumps leans against the coldest extremes. Humility helps. Baryons, the 5% storytellers, don't sit still. They flare, blow out, rain back, and stir galaxy centers. A burst of star formation can puff a cusp into a core. A quiet era can steepen it again. Disentangling what stars did from what the dark sector is doing takes patience and ensembles, not one-off heroes. The emerging view is a both-and. Realistic baryonic physics plus a small dose of warm. Smoothness or self-interaction. Softness can match the small-scale sky without upsetting the big symphony. Carry 3 images. The garden in a breeze. Cold plants every seed. The garden sprouts at all scales. Warm blows away the tiniest seeds, leaving a tidier bed. The crowded square. Collisionless passers-by keep the center packed and pointy. Self-interacting passers-by share space. The middle breathes and rounds. The sculpture in stages. Warm changes the block before the chisel. Fewer small grains to carve. Self-interactions reshape after the carving. Edges soften. Planes curve. So when you hear warm and self-interacting dark matter, translate it into something clear and human. Two gentle twists that leave the grand design intact while tending to the local texture. Warm trims the finest threads the universe could have woven. Self-interactions smooth the threads it did weave. With the honest weather of stars and gas, they help align the small with the large, the inner light with the outer frame, and the living sky with the scaffold that quietly holds it. What we know, a don't. Recap. Open questions and a question for you. What convinces you most? Step back from the details and take in the whole mural. We've walked through spinning disks and lensed arcs, baby picture ripples and cluster collisions, underground whispers and collider silence, small-scale quirks and large-scale triumphs. What, in plain human terms, do we actually know about the dark, and what remains honestly uncertain? What we know, with sturdy lines gravity's extra pull, is real and patterned. Galaxies rotate with flat outer speeds. Clusters weigh more than their light. Light itself bends more than visible matter allows. These effects repeat across systems and eras, and they fit together. The same hidden mass that steadies a disk also lenses background galaxies and helps glue clusters. The map matches the web. On the larger scales, the universe draws a foam of filaments, halos, and voids. Simulations of a cold, mostly collisionless component reproduce that web's layout and growth strikingly well, landing close to the observed counts of galaxies and clusters, and the statistics of the cosmic microwave background. The dark is quiet in the lab so far. Direct detection rooms haven't seen a definitive recoil. Colliders haven't caught a missing energy pattern that holds up. Telescopes haven't found a sky-bright glow that screams self-annihilation. Each non-detection is a boundary that trims the simplest, loudest versions of our favorite stories. Baryons matter, twice. Ordinary gas and stars both feel the dark scaffold and push back on it. Feedback from bursts, bars, and outflows can reshape inner halos, resolve some small-scale tensions, and explain part of the diversity among dwarfs, without breaking the large-scale match. What we don't know, with honest edges, what the dark is made of. Particle, wave, a family, heavy and quiet, light and chatty within its own sector. We have sketches, WIMPs, Axions, sterile neutrinos, warm flavors, self-interacting cousins, dark photons, and dark Higgses, but no confirmed portrait. How simple gravity is, everywhere. General relativity passes test after test, yet a few galactic-scale regularities tempt modified gravity accents. Most such accents struggle with lensing and the CMB, but the door to gravity plus a little more is not sealed, only narrowed. How the smallest halos live, how many exist, how many light lanterns, how often they grow cores, and how their satellites arrange themselves. These are moving targets that better data will pin down. Whether the dark talks to itself. Gentle self-interactions could soften centers and still respect clusters. Strong ones would have shown their hand. The allowed middle ground is shrinking but not gone. The case for the invisible majority, why many of us find it convincing. Picture 3 independent witnesses, none perfect, all consistent. Kinematics. Stars and gas moving too fast for the starlight's pull alone, in spirals, dwarfs, and clusters. Lensing. Background galaxies stretched and multiplied in proportion to mass you can't see, sometimes forming rings and arcs so clean they act as rulers. Early universe fingerprints. The microwave background's peak pattern and the Webb statistics point to a non-luminous mass that started cold and clumped early. These witnesses don't just point the same way, they quantify the same thing. Change one dial, add or subtract invisible mass, and all three react in step. That coherence is the spine of the argument. The best alternative, and why it's hard a gravity tweak can mimic parts of the rotation curve story with elegant economy. But gravity alone must then also reproduce strong and weak lensing patterns in complex fields. match the CMB's precise ripples, and recover the expansion-growth relationship across time, all while keeping Galaxies' messy physics in line. Some versions succeed locally but stumble cosmologically. Others work on averages but slip on detailed maps. Today's balance of evidence still favors extra mass plus standard gravity, with modest room for small, scale-dependent modifications. Open questions to watch and how they'll move. Composition. Are there Axion-like waves making fuzzy cores? Are there light-dark particles nudging electrons in new low-threshold detectors? Are there long-lived portal cousins leaving displaced decays at colliders or beam dumps? Interaction strength. Do dwarfs and clusters together fix a small but non-zero self-interaction? Do strong lensing substructure counts and stellar stream gaps match the number of small halos cold, dark matter predicts, or hint at warmth? Halo archaeology. Do planes of satellites persist once selection effects and orbits are nailed? Do field dwarfs with quiet histories still prefer cores? And how big are those cores truly? Consistency checks. Will Rubin, Euclid, Roman, and CMBS4 draw the same growth curve? Or will a controlled tension remain? One that points to dark complexity or gravity's accent? How the next wave tightens the net sharper lensing, cleaner redshifts, deeper time series. Wide-field surveys from ground and space will cross-calibrate shapes and distances, weigh halos tomographically, and stack signals until small systematics are dwarfed by statistics. New detection channels. Superconducting targets, crystals, superfluid helium, skipper CCDs, and directional gas chambers open windows to light, slow, or feebly coupled candidates that heavy nuclei miss. Long-lived hunts and intensity frontiers. Beam dumps, near detectors, flavor factories, and clever triggers chase faint portals with displaced or delayed signatures, the kind backgrounds hate to fake. Unified mocks and shared pipelines. The field is learning to observe the same simulated sky with multiple instruments, then compare answers before touching real data. Claims that survive that gauntlet deserve attention. A candid scoreboard strengths, coherence across methods, predictive large-scale power, flexible enough to absorb messy baryonic weather. Weaknesses: no incontrovertible non-gravitational detection yet, small-scale room for interpretation, model space still broad enough to hide in. Opportunities: next-gen maps and detectors target the remaining safe harbors. Cross-correlation culture reduces systematic blind spots. Nulls become as informative as signals. Risks: overfitting models to transient tensions, underestimating astrophysical complexity, mistaking pipeline quirks for physics. How to read claims without getting lost, ask for overlap. Does the hint show up in at least two independent channels? Say, a beam dump excess and a compatible rare decay. Check the knobs. If a single nuisance parameter shift erases the effect, treat it as fragile until cross-checks harden it. Prefer predictions. A solid claim stakes out a near-term test, not only a post-fit explanation. Common misconceptions quickly. It's just because we don't see all the dim stars. We count those. They fall far short of what lensing and dynamics demand. Dark matter must be one specific particle. It could be a family. Several minimal possibilities still survive. No detection means it's not there. No detection means this. Kind at this strength in this channel isn't there. Information that steers the search where a single result could swing the field adirectional underground detector, seeing an annual modulation that points to the expected wind. A displaced vertex signal repeated in two accelerators at the same mass and coupling, lensing substructure function from arcs and a stream gap function from the Milky Way that agree on the abundance of tiny halo stop, a persistent growth rate tension across Rubin, Euclid, Roman, and CMBS4 that survives all calibration games. How to think about no results. A clean no is a measurement. Each null slices the space of ideas, moving effort toward where nature might be hiding. When three independent no's trim to the same island, that island becomes the place to build. Discovery often looks like an island that refuses to sink as the tide of data rises. Your turn. View a Q&A prompt. You've heard the lines of evidence and the caveats. What convinces you most? Is it the way lensing draws mass where no light lives? The cosmic web matching simulations seeded with cold, unseen matter? The clean rotation curves that stay flat where starlight thins? Or do you lean toward a gravity tweak and want the next surveys to try to break the mass story? Drop your take in the comments. Which clue feels strongest? Which doubt feels healthiest? And what single measurement, lensing map, satellite census, lab recoil or collider trace would change your mind fastest? We'll feature a few responses in the next episode, stack them against fresh data, and let the quiet majority of the universe answer back. What's next? Step a little ahead in time. The telescopes are bigger, the cameras wider, the cryostats colder. The questions are the same. What is the dark stuff? How does it gather? How does it bend light? How does it steer the growth of galaxies? But the tools are about to sharpen in ways that turn whispers into measurable lines. 4 banners lead the parade. Rubin's legacy survey of space and time. Euclid, Roman, and CMB-S4. Together, they promise not a single knockout, but a weave of constraints tight enough to corner even a shy universe. Start with Rubin, LSST, the restless painter of the southern sky. Night after night, the same fields are revisited, each time a little deeper, a little sharper, until faint galaxies that were once suggestions become solid shapes. That repetition is the trick for weak lensing. The tiny stretching of galaxy images by foreground mass. Measure shapes of billions of galaxies, stack them across redshift slices, and you draw a 3D map of where mass lives and how it clumps with time. Rubin's strength is not one perfect exposure, but statistics plus cadence. The sheer number of sources, the ability to watch the sky change, and the control this brings over nuisances. Atmospheric blur, detector quirks, and the fickle colors of stars pretending to be galaxies. Out of that discipline comes a clean measure of the cosmic growth rate, the smoothness or lumpiness of the dark, and the way gravity lenses the faintest smudges at the edge of sight. Now turn to Euclid, the calm surveyor from space. Free of the atmosphere, Euclid trades cadence for stability. It measures shapes and distances with a steady hand, pairing high-quality imaging with slitless spectroscopy to place galaxies on a reliable distance ladder. That means lensing maps with fewer low-level distortions and a clustering ruler to match them. Where Rubin floods the zone, Euclid lays down a smooth floor. The comparison is powerful. Same sky, different systematics. If both tell the same story about the matter power on small and medium scales, confidence rises. If they diverge, the universe is teaching you something, or your pipelines are. Then Roman, formerly first, the precision brush. Think smaller area than Rubin, but Hubble-like resolution over huge swaths compared with Hubble's tiny keyholes. Roman's high-latitude survey will draw extremely sharp lensing maps and exquisite supernova light curves, and it will anchor photometric redshifts with space-grade calibration. The value here is purity and cross-calibration. Use Roman's crisp shapes to train the ground. Transfer that knowledge to Rubin's billions of galaxies and the full sky benefits. Roman also brings time domain and microlensing tricks that probe compact dark candidates and the structure of the Milky Way's halo from a fresh angle. Finally, CMB-S4, the next big ear tuned to the oldest light. The microwave background already gave us the universe's baby picture. What's next is the lensing of that baby picture by all the mass in between. With colder detectors and finer beams, CMB-S4 reconstructs a nearly all-sky map of projected mass that cares nothing about stars. That map reaches to high redshift, where galaxies are sparse, and it weighs structures that optical surveys only hint at. Combine CMB lensing with galaxy lensing and clustering, and you triangulate biases away. Where one probe is uncertain about galaxy physics, the other is not. What do these 4 do together? They cross-check gravity. If mass bends light the same way in all datasets and at all epochs, then modified gravity detours must thread a very narrow path. If not, you catch the first cracks where the law changes tone. They nail growth versus geometry. Euclid and Roman fixed distances and expansion history cleanly. Rubin and CMB-S4 fix structure growth and the lensing strength. A real tension between these tells you whether the universe is simply coasting in a smooth, dark energy sea, or whether the dark matter itself, or gravity, is playing a deeper game. They push small scales. The shape of lensing and clustering on the smallest usable angles probes how warm, self-interacting, or otherwise non-cold the dark might be. With sharper PSFs, better redshifts, and smarter deblending, the surveys reach scales where warm, edges blur and self-interactions soften cores without trusting any one galaxy. Model too much, they map the web in 3D, cross-correlate galaxy shapes with CMB-S4's mass map, stack lensing around voids, clusters, and filaments, follow how halos grow with time. The result is a web not only seen but weighed, cell by cell. All of that depends on systematics being tamed, not wished away. The teams are building a common playbook, shape calibration by simulation and by image realism. Inject fake galaxies into real images. Recover them with the same tools used on the sky, and measure the bias directly. Photometric redshifts checked by spectroscopic subsets and by clustering redshifts, where angular cross-correlations between known and unknown samples reveal the true distance mix. Blending and selection handled with multi-band, multi-resolution fits, letting Roman or Euclid untangle knots that are smeared to the ground. Shear position couplings and intrinsic alignments modeled with data-driven templates and then marginalized over, rather than swept under. Unified simulations, mock skies that include galaxies, stars, weather, optics, electronics, and the messy habits of pipelines, so you can observe the same truth with different instruments and see if the answers agree. What new limits are within reach? Self-interaction strength pushed down by weighing clusters and the small-scale lensing of group halos, while checking that dwarfs and filaments tell the same tale. Warmth or fuzziness of the dark, constrained by the cutoff in small-scale power. Read from high Z lensing and strong lensing substructure counts, now with far better statistics. Halo profiles mapped from the inner kiloparsec to the outskirts by stacking millions of galaxies and clusters, testing cusp-to-core transitions without committing to any one feedback recipe. Neutrino lightness pressed harder by the imprint neutrinos leave on the growth of structure, with CMB-S4 setting the scaffold and Rubin Euclid Roman filling in the walls. You'll also see new cartography. Shear selected clusters without relying on X-ray or optical richness. Tomographic void catalogues used as clean cosmology rulers. Subhalo inventories from strong lensing arcs measured by Roman's resolution, then compared to stream gaps around the Milky Way. Each catalogue is a different dialect of the same language, mass talking through light, and the translation improves when the dictionaries are shared. What would success feel like? A concordance map, Rubin's tomographic lensing, Euclid's shapes and distances, Roman's sharp anchors, and CMB-S4's projected mass, all drawing the same growth curve within honest errors. A small-scale verdict. Either the cold picture survives down to new, tinier cells of the web, or a subtle softening appears that is too persistent to be baryonic trickery alone. A portal squeeze. Indirect and collider hints must pass tighter cosmic filters. Many once roomy dark sector models discover their parameter space trimmed to slivers that still fit the sky. A surprise. An internal tension that refuses to fade with better calibration. Perhaps a lensing amplitude modestly off from expectations, or a time-dependent pattern in growth that doesn't sit comfortably in the standard chair. The point is not to hope for a mismatch. It is to build measurements so clean that if nature offers one, you'll trust it. 3 threads will make the difference. First, cross-correlation as a habit. Don't analyze each survey in isolation and compare at the end. Interlock the datasets from the start. Use Roman to calibrate Rubin shapes. Use Euclid redshifts to steady Roman lensing. Use CMBS4 to anchor mass where galaxies are scarce. The errors shrink and the blind spots overlap less. Second, transparency and shared mocks. Release image cutouts, masks, PSF models, and end-to-end simulations, so independent teams can try to break the result. A claim that survives outside its home pipeline earns trust. Third, humility about models. Where galaxy physics is loud, lean on lensing and clustering combinations that minimize those voices. Where it cannot be avoided, let nuisance parameters float and pay the cost in precision rather than buying false accuracy. Carry 3 images as you look ahead. The loom. Rubin, Euclid, Roman and CMBS4 are the warp and weft. Run them together, and a pattern appears that no single thread could hold. The scale and the plumb line. Galaxies are the scale. Pretty, useful, but fussy. CMB lensing is the plumb line, simple, austere. When both agree, the wall is straight. The lantern parade. Each survey brings its own light, fast and wide, calm and steady, sharp and deep, cold and ancient. Walk them in step and the path through the dark is lit from all sides. So what's next? Not one silver bullet, but a concert. 4 instruments tuned to the same score, rehearsed to play together, and ready to turn the invisible majority from a sketch into a portrait with lines crisp enough that even a quiet universe will have to speak plainly. Why baryons aren't enough. Stars, gas, dust, black holes. Add them up, still short. Start with a simple act. Take the universe's ledger and begin counting only what talks to light. Count the stars that shine and the remnants that no longer do. Count the clouds of gas, cold and quiet, hot and loud. Count the fine dust that turns starlight amber. Count the black holes at the centers of galaxies and the smaller ones seeded by dying stars. When you add that entire luminous family together, you expect the total to match the gravity you measure. It doesn't. Even after a generous count, you're still short. Baryons are the familiar stuff. Protons and neutrons wrapped with electrons, building atoms, molecules, people, planets, and stars. Because baryons interact with light, they leave multiple trails. They glow as stars. They absorb and emit as gas. They redden and scatter as dust. Even when they hide, we have ways to tease them out. That's why this chapter is honest from the first line. If ordinary matter were enough, we would have found it by now. Begin with stars. Their light lets us estimate how much mass they hold. We calibrate the brightness of old and young populations, tally the faint dwarfs, and account for stellar corpses, white dwarfs, neutron stars, and the quiet ashes of supernovae. However you slice the census, the starlight plus the dead light is not nearly heavy enough. Galaxies need far more pull in their outskirts than their stars can supply. Low surface brightness galaxies make the point even sharper. They're dim by design, yet their outer regions still move with confidence that only a deep, unseen halo can explain. Turn to gas. Cold atomic gas can be traced by a humble radio whisper. Molecular gas hides more cleverly, but it gives itself away through companion molecules that broadcast at specific wavelengths. Hot gas in galaxies and clusters announces itself in high-energy light. When you count all these reservoirs, cold, warm, and hot, you do move the needle. In clusters especially, hot plasma is a major share of the visible matter. And yet, even there, the gravity you infer from motions and from light bending outweighs stars plus gas by a wide margin. The bowl that holds the cluster is deeper than baryons alone can dig. Dust? It's beautiful, but it is not a heavy accountant. Grains, veil and color, sculpting the look of a galaxy, but their mass contribution is small. You can add dust in, and you should, but it won't rescue the balance sheet. What about black holes? The monsters at galaxy centers feel promising, enormous, mysterious, compelling. But their mass, compared with the whole galaxy, is modest. A central giant might weigh as much as a few tenths of a percent of its host stars. In the grand total, that is not enough to anchor the outer orbits or to explain cluster-scale pulls. Stellar mass black holes are more numerous, but spread across a galaxy, they still cannot shoulder the missing mass. Surveys that look for sudden brightenings of background stars, caused by compact dark objects passing in front, have already searched for a hidden population of faint, heavy bodies in galactic halos. The result is firm. There are not enough such compact objects to account for what's missing. Maybe, you think, ordinary matter is simply hiding in hard-to-see forms. There is truth in that thought. A portion of Baryons slips the net of easy detection. Some live in the thin, warm-hot fog between galaxies. Some sit in the vast, faint halos of gas around galaxies, the circumgalactic medium, too diffuse to glow brightly, but real enough to sip starlight and leave fingerprints. Astronomers have worked for years to track down these missing baryons of the visible world, and many have been found. The surprise is that even when you add them, you still fall far short of the total gravity the universe displays. The missing baryons problem is a bookkeeping issue inside the small slice of ordinary matter. The missing mass problem is larger. It points beyond the slice itself. 3 lines of reasoning make that conclusion hard to escape. First, the baby picture of the universe, the faint, dappled microwave glow, carries the recipe of early matter. Its pattern prefers only a small dose of ordinary matter. If you try to stuff far more baryons into the recipe, the rhythm of hot and cold spots goes off key. The snapshot would not look like the one we actually see. Second, the chemistry of the first minutes set the amounts of light elements. Hydrogen's heavier cousins and helium's lighter cousins. Those delicate ratios are sensitive to how many baryons existed back then. The observed mix speaks clearly. There were not enough baryons to become the entire gravitating substance later. Raise the baryon count too high, and those early chemical fingerprints would be wrong. Third, the growth of structure itself gives an answer. Before the fog of the early universe cleared, ordinary matter was leashed to light. It sloshed and rang like a springy fluid. A cosmos built only from that springy fluid would have struggled to plant early, deep seeds for galaxies to grow from. The bright matter would have kept smearing its own small clumps away. The universe we inhabit formed a rich web of structure on time. That asks for a quiet partner that felt gravity, but not the slosh. Something to lay down wells early and hold them steady while light-tide matter caught up. Behavior, not just totals, seals the case. Baryons collide, heat, cool, and radiate. They experience friction. In a cosmic fender bender like the bullet cluster, the hot gas slams to a halt and glows between the passing swarms. But the strongest gravity follows the galaxies that sailed through, unchoked by drag. If the main mass were baryonic gas, the centers of gravity would sit with the glow. They do not. The peaks of pull align with what does not collide. Maps sharpen the picture. Strong lensing around galaxies and clusters, rings and arcs, often demand more weight than the light can justify, and they reveal small, dense clumps that don't have bright counterparts. Weak lensing across wide fields draws a web that spreads beyond luminous filaments. In both cases, the mass map is broader and heavier than the light map. Baryons like to cool into disks and clumps. The main halo does not. Its reach is wide, its edges soft, its grip steady. Signatures of something that does not shed energy by shining. You can test the all-baryon idea from another angle. Try to build a universe with only ordinary matter and tweak the rules of gravity to compensate. You may fit one corner of the story, a rotation curve here, a galaxy there, but other corners come loose. The baby picture's rhythm rebels. Colliding clusters refuse to line up. The delicate preferred spacing imprinted in the galaxy distribution loses its timing. A patch saves one wall and opens a crack in another. The simplest reading stays in view, a small luminous share that speaks with light, and a larger, quiet share that carries most of the weight. This does not make baryons unimportant. The 5% slice is where complexity blooms. Stars, chemistry, worlds, and questions. Baryons are the storytellers. Dark matter is the stage. One cannot replace the other. But when the question is, who is doing the holding, ordinary matter steps back. It brightens the scene, stirs the air, and sculpts the local details. The deeper embrace belongs to something that does not glow. Keep 3 clear images for your narration. First, the household budget. You count the obvious bills, rent, food, lights, and then discover a larger steady charge you had not seen. It explains why your account kept running low. Stars, gas, dust, and black holes are the obvious bills. The unseen mass is the steady charge shaping the bottom line. Second, the orchestra. Woodwinds, brass, and strings are the bright voices. You can point to them, but the floor's deep resonance, the thing that makes the hall vibrate, comes from a quieter structure you don't notice until it's gone. Baryons make the melody. The unlit mass provides the resonance. Third, the lantern and the glass. The flame is visible and lively. The glass globe is dim but decisive. Take away the globe, and the flame flickers and fails in the wind. The halo is the glass, wider than your eye first assumes. So when you hear, "Baryons aren't enough," translate it into something human and clear. We have counted the things that shine, and the things they become when they stop shining. We have counted the gases and the dust. We have counted the giants at galactic centers, and the small dark embers scattered through disks. Even with a generous tally, the universe's gravity calls for more. The shortfall isn't a rounding error. It is the main story's quiet half. In the chapters ahead, we'll sit with leading ideas for what that quiet half might be, and how new instruments are trying to listen for it directly. For now, the conclusion is steady. Stars, gas, dust, and black holes are the furniture in the room. The walls, the thing that holds the room together, are made of something we cannot see. Why galaxies need halos. Disks, bars, and star formation histories stabilized by massive halos. Picture a spiral galaxy from the side, a thin, bright disk, dusty lanes, blue knots of young stars, a hushed bulge in the middle, and around everything, an unseen halo. The disk is the performance. The halo is the stage. Without that stage, the show stumbles, scenes rush, props wobble, and the finale comes too soon. With it, the acts flow and the story lasts. Start with the simplest job, a deep, smooth, gravitational well. Gas and stars in a disk want to clump and fragment. Feedback from newborn stars kicks the gas. Turbulence stirs it. Gravity tightens it again. A massive halo lowers the floor beneath the disk, spreads gravity over a wide radius, and slows the worst runaways. Instead of shattering into a few giant clumps that quickly merge, the disk can settle, rotate, and grow organized structures, spirals, rings, and bars, without tearing itself apart. The halo also keeps the spin. A forming galaxy gains angular momentum from the cosmic web, but cooling gas would love to shed it and plunge inward. The halo acts like a flywheel, storing most of the system's angular momentum and trading it gently with the luminous parts. That exchange lets the disk spread instead of collapse, keeping spirals thin and extended while the inner regions form stars. Now the bar, that bright, elongated feature in many disks. A bar is a test of balance. It channels gas inward, rearranges orbits, and can feed the center. With no partner to absorb angular momentum, a bar either overheats the inner galaxy or dies young. A live halo is the partner. It takes, and later returns, angular momentum, letting the bar grow, slow modestly, and persist for billions of years. In that steady state, the bar becomes an engine, building inner rings, seeding new spiral arms at its ends, and regulating central growth rather than choking the disk. Spiral density waves also lean on the halo. Because the halo keeps outer rotation from dropping sharply, spiral patterns can maintain coherence far beyond the bulge. That extended support gives gas time to pile up along the crests, shock, and form stars, so arms remain visible and productive instead of shearing into tatters. The halo calms the weather. Gas does not arrive as a single pore. It drips along filaments, falls in clumps, and brings small companions. The halo catches and slows this traffic, mixing it before it reaches the disk. It also serves as a reservoir. Outflows from supernovae and central winds rise into the halo's warm, hot atmosphere, cool, and rain back as a galactic fountain. That recycling changes boom and bust into a gentler rhythm, smoothing star formation over time. At the edges of disks, thin gas, strong shear. Stability is fragile. A generous halo sets a rotation profile that discourages runaway fragmentation. Clumps still form, but they knit into arms and knots the disk can digest. Where the outer halo is light or truncated, fringes warp and fray. Clumps grow too large. Outer disks tilt or fade. During encounters and minor mergers, the halo is a shock absorber. Infalling satellites dump most of their orbital energy into the dark outskirts instead of the bright disk. Tidal debris spreads through the halo. The disk wobbles but survives. A massive extended halo also sets the leash on. Satellites, how fast they sink and how hard they jolt the host. Protecting. Thin disks through many small collisions. Wrapped. Inside the halo is the circumgalactic medium, CGM. A vast, faint atmosphere at many temperatures. In a sufficiently massive halo, the CGM stays bound and partly hot, fueling the disk on schedule rather than all at once. Cool clouds condense and fall. Hot layers hold back collapse where the disk would otherwise ignite too quickly. Feedback from starbursts or a central engine can heat portions of this gas, nudging the system toward balance without fully quenching it. The halo is the dial between famine and feast. Shape and concentration matter. A rounder inner halo yields calmer, more symmetric inner orbits. Elongated inner halos nudge disks toward lopsidedness and one-armed spirals. A tightly concentrated halo piles mass early and deep, encouraging earlier bars and stronger bulges, while a more extended halo favors later, open spirals. Even the thick disk, the puffier, older layer above the thin plane, remembers the halo's grip, where minor mergers and early turbulence met a sturdy halo. The thick disk grew broad but orderly, and the thin disk later slid back in on the same scaffold. Red star formation histories as weather logs. In shallow halos, typical of dwarfs, histories look gusty, sharp bursts, long pauses, easy quenching after a nudge. In robust halos, the record smooths. Bars and arms still trigger local flares, but a base level persists, set by recycling in the CGM and the disk's regulated response. Metallicities and ages grade gently with radius. Outer disks keep forming stars long after the bulge has matured. Even quenching depends on halos. Above a threshold mass, halos can sustain hot CGM that cools slowly. The disk's fuel dwindles and star formation fades. Intermittent heating from a central engine can hold the line for eons. In lower mass halos, that kind of long quiescence is harder. Cosmic inflow and recycled fountains keep nudging the disk back to work. Two contrast sketches help fix the idea. No serious halo. The disk spins up, clumps grow huge. The center overfeeds early, and the next infall hits hard. Bars sputter, spirals shear, outer parts warp. Star formation whipsaws between famine and flood. With a massive halo, early clumps are moderated. A bar finds a partner to trade momentum with. Spirals keep time to large radii. Fountains recycle. Minor mergers bruise but do not break. The star formation log reads in long, calm sentences. Halos also explain diversity. Two galaxies with similar stellar mass can look different because their halos differ in mass, shape, or history. Slightly heavier halos stabilize thinner disks and slower bars. Slightly lighter ones invite a clumpier youth and earlier, stronger bars. The law is the same, but the dial settings differ. A few case sketches. Barred spirals. Long, steady bars imply halos that can absorb angular momentum without overslowing the pattern. Inner rings and star-forming spurs follow, and the center grows in measured steps. Low-mass dwarfs. Shallow halos invite bursty lives. A feedback episode can stir the entire inner region. Slightly heavier halos turn flicker into hum. Gas-rich giants. Extended halos keep outer rotation flat, letting spiral structure and star formation reach astonishing radii. So why do galaxies need halos? Because order needs a frame. The halo doesn't write the melody, the disk does, but it holds the tempo, keeps the beat steady, and gives the song room to soar without screaming. It turns a bright, brief solo into a long, coherent symphony. Carry three images, the stage and the play. Bars lead, spirals sing chorus, stars dance. The halo keeps the floor from buckling. The flywheel. The disk tries to spend its spin too fast. The halo stores surplus and feeds it back slowly. The weather map. Storms of inflow and outflow pass through. The halo breaks squalls, recycles rain, and turns flash floods into a climate you can live in. When you hear galaxies need halos, translate it simply. Disks stay thin. Bars work as engines, not wreckers. Spirals keep time far from the center. And star formation writes long sentences, not shouts, because a massive, quiet partner holds the space where the visible can make its art. WIMPs and Freeze-Out. Picture the early universe as a bright, crowded train station at rush hour. Everything is hot and close. Particles are bumping shoulders, exchanging tickets, stepping on and off trains without pause. In that crush, a certain kind of passenger, call them WIMPs, short for weakly interacting massive particles, moves with the crowd like everyone else. They meet often. They pair up, disappear, reappear, trade partners, and blend back into the bustle. Nothing about them is special yet. They're just part of the flow. Now let the station slowly cool and empty as time passes. Trains come less often. The platforms spread out. Those same WIMPs still meet, but less frequently. At first, the old pattern holds. Whenever two WIMPs collide, they can turn into ordinary particles. And the ordinary particles in the crowd can collide and make WIMPs again. Give and take keeps the head count steady, but cooling changes the rhythm. Encounters grow rarer. A moment arrives when the making can no longer keep up with the unmaking. From that point on, the number of WIMPs that remain is basically locked in. They have fallen out of the crowd's rhythm. They have, in the language of cosmology, frozen out. Freeze-out is less dramatic than it sounds. No ice forms, no shattering happens. It's simply the moment when the universe expands and cools enough that certain reactions stop happening often enough to balance the books. Before that moment, WIMPs were in step with everything else. After it, they become leftovers, relics of a busier time. They keep riding the universe out to the present, quiet and persistent, responding to gravity and almost nothing else. Why does that matter? Because if WIMPs have the kind of shyness the name suggests, rarely interacting with ordinary matter, but not impossibly rare, then the amount that survives after freeze-out turns out to be just about what we measure for the dark matter today. That coincidence has a nickname, the WIMP miracle. Miracle here doesn't mean magic. It means surprisingly natural. If you assume a particle with a mass in a familiar range and a tendency to bump into things at about the feeble rate the weak force allows, you end up with the right cosmic abundance without forcing the numbers. You press play on the hot early universe, and you simply get the amount of dark matter we observe. Hold the idea by walking through three eras. First, the soup era. Temperatures are so high that distinctions blur. Creation and destruction of WIMPs happen constantly, balanced by the crowd. In this era, asking, how many WIMPs are there, is like asking, how many people are standing still in a running river? The answer keeps changing. Everything mixes. Second, the balance-breaking era. The universe expands, temperature falls. Ordinary particles don't have enough energy to keep remaking WIMPs at the old pace. Two WIMPs can still find each other and vanish into lighter particles when they collide, but they meet less and less. The balance tilts. The river slows. Third, the relic era. Encounters have become so rare that the number of WIMPs stops changing in any meaningful way. From then on, they coast. They do not glow. They do not stick to atoms, and they barely notice the electromagnetic fuss that lights the stars. They simply build up in the places gravity guides them, and over billions of years they gather into halos, filaments, and clusters, the quiet scaffolding of the visible sky. Now, the gentle heart of the miracle. Imagine a dimmer switch that sets how often WIMPs bump into each other. Turn the switch up so they collide more frequently, and more of them disappear before freeze-out locks the number in. You end with too few. Turn the switch down so they collide less, and too many survive. You end with too many. There is a just right setting where the leftovers match the dark matter we measure. That setting lands near the very scale of feebleness already known from a familiar force of nature. It's as if the universe chose a common, well-tested dial position and with no extra tricks, delivered the right amount of invisible mass. That is the tidy appeal people mean when they say WIMP miracle. You can feel why this is so tempting. It ties the grand, slow story of the cosmos to the small, quick story of particle physics. It says, if there exists a heavy, shy particle with a personality not too different from things we already know, then the early universe will naturally leave behind exactly the portion we need to hold galaxies together today. The dark matter's abundance becomes a fossil of how sociable it once was. From this story, a set of searches follows like stepping stones. If WIMPs still occasionally bump into ordinary matter, even very rarely, then a large, quiet detector on Earth might catch a soft tap, a small flash or a tiny whisper of charge as a passing WIMP nudges a nucleus. That's the logic of underground experiments that wait in the dark and count only the cleanest signals. If WIMPs still occasionally bump into each other in places where they are dense, near galactic centers, or in the hearts of dwarf galaxies, then they're rare. Disappearances might produce telltale light, faint excesses of gamma rays, or a sprinkle of unusual particles that telescopes and satellites can notice against the background. That is the logic of indirect searches that watch the sky for the faintest leftovers of an ancient habit. If WIMPs can be made in the first place, perhaps we can make them on demand. By colliding ordinary particles at extreme energy and seeing whether something heavy and quiet slips away, leaving missing momentum in the wreckage. That is the logic of accelerator hunts. In each path, the same idea is tested from a different angle. A thermal relic should leave footprints, however delicate, that match its shy personality. It's important to be honest about where we are. The hunts have not found a clear WIMP signal so far. The big silent rooms under mountains have grown huge and almost impossibly pure. Space and ground-based telescopes have stacked years of careful observations. Colliders have studied collisions by the trillions. With each pass, broad, hopeful spaces on the map have been crossed out. That might mean WIMPs are lighter or heavier than we expected. It might mean their shyness is tuned differently than the simplest story assumed, or it might mean the dark matter took another path entirely. The miracle was a clue, not a guarantee. Even so, the freeze-out picture is valuable beyond any one candidate. It teaches a method. The early universe was a factory that set the inventory for today. If a particle was once part of the thermal crowd, its abundance now encodes a memory of how often it interacted then. Change the shyness, change the leftovers. That link between micro-behavior and macro-abundance is one of the cleanest bridges we have between particle physics and cosmology. Whether the winning key is a classic WIMP, a neighbor with a different kind of feebleness, or something surprisingly new, the bridge remains. You can hold the idea with three images. Think of a bustling bakery at dawn. Ovens roar, trays fly, loaves appear and vanish into bags. As morning passes, the rush eases. At a certain quiet point, the bakers stop taking new orders. Whatever sits on the shelf then is the day's remainder. That's freeze-out. The size of the remainder depends on how fast goods moved when the shop was busy. Think of a dance floor. Early on, partners are constantly switching. No one stands alone. As the music slows and people drift home, a moment comes when swaps mostly stop. Whoever is still paired stays paired. Whoever is alone remains alone. That final arrangement is the relic population, set by how vigorous the swapping was before closing time. Think of snowfall. Flakes melt when they hit warm ground. As the air cools toward evening, melting slows. At some hour, it no longer keeps pace with the fall. Whatever lands from that hour on begins to stick. The depth in the morning remembers when the balance tipped. So when you hear WIMPs and Freeze-Out, or the WIMP miracle, translate it into something clear and human. In the hot beginning, everything mixed. As the universe cooled, certain reactions fell out of step. A leftover population endured. If the particle's shyness sat near a familiar dial setting, the amount that endured matches the dark matter we measure today. It's a neat hint, one that inspired a generation of searchers and still guides new ones. And if, in the end, the universe chose a different key, this chapter will have done its deeper work anyway. It will have shown you how a young cosmos writes its habits into the present, and how a gentle idea, leftovers from a crowded hour, can help explain why the stars still hold their circles after all this time. Thank you for spending these minutes with me tonight on Silent Equations. Before we part, I'd love to hear from you. Tell me 3 quick things in the comments: your city, your time of day, and your sky in one word. It might look like Lisbon 2310, clear, or Manila, morning, hazy. Seeing our little constellation of listeners appear across the map is my favorite part of this channel. What stayed with you from this episode? Share one sentence you'd tell a friend tomorrow. Was it a fact, a feeling, a picture you'll carry when you look up again? If you drifted off and you're catching the end in the morning, say hello and leave the time you woke up to this. Night crew and day crew, you're both welcome here. Choose our next journey with a tiny vote. Type A if you want auroras, how the sky learns to dance. Type B for reading starlight, how spectra tell the truth. I'll check the comments and follow your lead. If you learn something new, tap like. It really helps this calm corner reach the next person who needs it. If you want more nights like this, subscribe and ring the bell. Set it to all, so the next episode finds you wherever you are. On a bus, on a couch, under a sky you can see, or a sky you're still searching for. I read everything you write, so tell me how you listen. Are you walking, studying, winding down, holding a sleepy baby, working a night shift? What's one small ritual you pair with these stories? A cup of tea, a candle, a blanket, a window cracked open to the cool air. I'll borrow your favorites for future intros so we can share ideas for calm. If you want company while you rest, the playlist on the channel called Sleep Editions waits for you. Hours of gentle astronomy stitched together without mid-rolls. If you'd rather keep learning, start with the first episode in the star life cycle. You can also find sources and extra reading in the description if you like to go down friendly rabbit holes. Before we go, let's take one last easy breath together. In for 4, 1, 2, 3, 4. Out for 6, 1, 2, 3, 4, 5, 6. Let your jaw soften. Let your shoulders drop a notch. The sky will keep its watch until you're ready to look up again. Thank you for being part of Silent Equations. I'm grateful for your time, your attention, and your stories. Leave your location, your skyword, and your vote for the next topic below. I'll see you in the comments, and then back here soon for another quiet adventure. Good night, good morning, and keep looking up.